There is a silence in the mathematics of the universe, a stillness that unnerves those who listen closely. Because the numbers that govern existence, the force that binds atoms, the rate at which space stretches, the mass of particles too small to see, appear calibrated with a precision that defies comfortable explanation. The gravitational constant, woven into the collapse of clouds that birth stars, holds a value so exact that if it differed by even 1 part in 10 to the power of 50, galaxies would never congeal from the primordial dark, and stars would burn too fast or fail to ignite at all. The cosmological constant, that whisper of energy embedded in the vacuum itself, measures around 1 part in 10 to the power of 120, a number so improbably small that physicists expected it to be 50 or even 120 orders of magnitude larger. Yet it sits precisely where it must for space to expand gently enough that matter can gather into structures capable of hosting chemistry, memory, and thought. If this constant were only slightly greater, the universe would have torn itself apart before the first atoms could form. If slightly less, gravity would have crushed everything back into a singular point within cosmic moments. The strong nuclear force, binding protons inside atomic nuclei against their electromagnetic repulsion, tolerates a margin of just 2%, stronger, and hydrogen would fuse into helium everywhere at once, leaving no water, no fuel for long-burning suns, weaker. And no element heavier than hydrogen could ever exist, rendering the periodic table a one-entry list and biology an impossibility. These are not approximations or poetic exaggerations. They are the constraints written into observation, into the cosmic microwave background's fluctuations, into the distribution of galaxies across billions of light years, into the lifespan of stars and the existence of carbon. That fragile element forged in stellar cores only because a resonance level in its nucleus sits within a narrow window between 7.596 and 7.716 million electron volts, tuned as if by invisible hands to allow the universe to build the molecules of complexity. Yet the feeling of intentionality may be nothing more than the mind's ancient habit of seeing faces in clouds, patterns in randomness, agency in the mechanical turning of gears. We are pattern-seeking creatures, shaped by evolution to detect predators in rustling grass and meaning in the trajectories of falling stones. So perhaps it is no surprise that when we encounter a universe whose constants permit our existence, we interpret that permission as purpose, as design, as a cosmic architecture with ourselves at its center. The anthropic principle reminds us that we could only ever find ourselves in a universe capable of producing observers. In all the hypothetical universes where the constants fell differently, there would be no one to notice their sterility, no consciousness to ask why the numbers came up wrong. Perhaps there is no deeper mystery here than survivorship bias writ cosmically large, a trick of perspective where the only universe we can measure is the one fine-tuned for measurement itself. But there is a deeper problem. If the constants are arbitrary, if they could have taken any value across an infinite range, if the odds of them landing within the knife-edge parameters necessary for stars, planets, chemistry, if life become not merely unlikely but so staggeringly improbable that invoking chance feels less like an explanation and more like an evasion, a refusal to follow the evidence toward conclusions that unsettle our assumptions about randomness and necessity. Here a question emerges, quiet but insistent, beneath the surface of equations and observation. What if the universe is not simply permitting life, but is structured in such a way that life, consciousness, if the capacity to understand are woven into its foundational logic, not as accidents, but as expressions of something deeper? Some physicists propose a multiverse, an infinity of parallel realities where every possible combination of constants plays out. And we find ourselves in this universe simply because it is one of the rare pockets where the numbers allow us to exist, a cosmic lottery where we hold the winning ticket not because the game was rigged, but because countless tickets were drawn and most led to empty, lifeless voids. Yet this explanation, while mathematically seductive, raises its own mysteries. If the multiverse is real, what determines the distribution of constants across those infinite realms? Well, does that distribution itself require fine-tuning to ensure that at least some universes fall within life-permitting ranges? Others suggest that a more complete theory, a unified framework that merges quantum mechanics and gravity, might reveal that the constants are not independent dials, but interconnected variables constrained by a single deeper principle, reducing the apparent fine-tuning to an inevitable consequence of a more fundamental law we have not yet discovered. This possibility is tantalizing, yet it does not eliminate the question so much as relocate it. Why should that deeper law exist at all? And why should it be the kind of law that permits complexity, structure, and the emergence of beings capable of contemplating their own origins? The galaxies themselves seem to know something we do not, arranging across the cosmos in filaments and voids that trace the gravitational echoes of quantum fluctuations from the first fraction of a second after the beginning, a pattern so delicate that if the initial density variations had been slightly smoother, matter would never have clumped into stars and planets, and if slightly rougher, the universe would have collapsed into black holes long before the first light could travel across space. Inflation theory, which proposes a brief exponential expansion in the universe's infancy, predicts precisely the spectrum of fluctuations we observe in the cosmic microwave background. Yet inflation itself requires fine-tuning to begin and end at the right moments, suggesting that the explanation of one fine-tuning may rest on another, an infinite regress of calibrations, each demanding its own account. The vacuum, that supposed nothingness between particles, seethes with quantum fields whose energy should, according to every calculation, dominate the cosmos and tear space apart. Yet something, some unknown counterbalancing term, cancels this vacuum energy to a precision of 120 decimal places, leaving only the faint residue we call dark energy, just enough to accelerate expansion without destroying structure. This cancellation is so exact, so improbable, that it has been called the worst prediction in the history of physics, not because the theory is wrong, but because the theory predicts the right outcome only if an invisible term exists to perfectly counteract a number that should be catastrophically large. And this is where the story bends. The laws of nature, as we know them, contain not just the capacity for stars and chemistry, but also the capacity for discovery, for minds to arise that can decode the cosmic microwave background, measure the masses of distant galaxies, as infer the existence of dark matter and dark energy from the motion of things they cannot see. Intelligence, in this view, is not merely a byproduct of fortunate constants, but a feature of a universe that seems almost designed to be understood. As if the cosmos were not just life-permitting, but also comprehensibility-permitting, offering clues to its own structure through the regularity of physical law and the accessibility of evidence written in starlight and gravitational waves. Perhaps this is the deepest fine-tuning of all, not that the universe allows observers to exist, but that it allows observers to understand, that it is the kind of universe where mathematical patterns in human minds correspond to patterns in the fabric of space and time. But equations carved on paper can predict the behavior of particles and the evolution of galaxies across billions of years. This correspondence is so uncanny, so unexpectedly powerful, that it has led some to wonder whether consciousness and cosmos are not separate phenomena, but two aspects of a single reality. Whether the universe's ability to know itself through minds like ours is not an accident of chemistry, but a clue to the nature of existence itself. Yet the truth may be stranger than either design or accident, hovering in a space where those categories lose their meaning. If the constants are truly arbitrary, then fine-tuning is a puzzle that demands explanation, whether through multiverses, deeper laws, then something else entirely. But if the constants are necessary, then they could not have been otherwise. Then the appearance of fine-tuning dissolves, replaced by the question of why necessity should take this particular form, why the inevitable should be so conducive to complexity and awareness. The cosmological constant, the strong force, the mass of the electron, the rate of expansion, all these numbers could have been different, at least as far as our current theories allow. Yet they are not. And the universe that results is one where hydrogen fuses into helium in the cores of stars, and carbon and oxygen emerge from stellar deaths, and planets cool into solid worlds with atmospheres and oceans, and molecules fold into structures capable of replication and mutation. And nervous systems wire themselves into networks that generate sensation, memory, language, and the ability to look up at the night sky and ask, with a mixture of wonder and unease, why the darkness is punctuated by light. The feeling of design is not proof of design, and neither is it proof of its absence. And in the space between these poles lies the central tension of existence. The universe behaves as if it were built for something, yet the builder, and there is one, leaves no signature beyond the eerie precision of the constants themselves. Perhaps the design is real, the work of a mind or force or principle that transcends the physical laws it authored, a cosmic architect whose intentions are encoded in the ratios of fundamental forces and the initial conditions of the Big Bang. Or perhaps the design is illusory, a cognitive artifact born from the fact that we can only ever observe a universe compatible with our existence, and any sense of purpose or intentionality is merely the projection of our own need for meaning onto an indifferent cosmos that feels designed only because we are here to feel it. Or perhaps the truth is neither of these, but something more subtle, a universe that is neither designed nor random but self-organizing, whose laws contain within them the seeds of complexity and consciousness, not because they were tuned by an external hand, but because the nature of reality itself, at its deepest level, is such that structure and awareness emerge inevitably from the interplay of matter, energy, space, but time. The question, then, is not only whether the universe is fine-tuned, but what it means if it is. But what it means if it is not. If fine-tuning points toward design, then we are left to wonder about the nature of the designer, whether it is a conscious agent, a mathematical necessity. Then something stranger still, then whether the universe's capacity to produce beings who can question its origins is itself part of the design or an unintended consequence. If fine-tuning is explained by a multiverse, then we are left to confront the vertigo of existing in one bubble of reality among an infinity of others, most of them dead and dark, then to ask whether our universe's hospitality to life is rendered meaningless by its rarity or made more precious by it. If fine-tuning is an illusion born from incomplete theories, then we are left to hope that the deeper laws waiting to be discovered will not merely shift the mystery, but resolve it, revealing a framework where the constants are not arbitrary dials, but necessary expressions of a unified truth. Then that hope itself may be a kind of faith, a belief that the universe owes us an explanation that satisfies both our mathematics and our longing for coherence. What we know is this: the universe exists, then it permits us to exist within it. Then the margin by which it permits this is so narrow that a shift of a few decimal places in any of several fundamental constants would render it hostile to stars, chemistry, then thought. What we do not know is whether this narrow margin is a clue or a coincidence, whether the precision we observe is evidence of intention or merely the selection effect of a universe that could not be otherwise and still contain observers to notice. The design illusion, if it is an illusion, is a powerful one, woven into the fabric of space and time, into the forces that bind quarks into protons and protons into nuclei, and nuclei into atoms and atoms into molecules and molecules into cells, and cells into brains capable of modeling the cosmos and wondering why the model works. And if it is not an illusion, if the appearance of design reflects a deeper order we have not yet understood, if the universe's eerie precision is not a puzzle to be explained away, but a message to be decoded, a whisper from the foundations of reality suggesting that existence is not an accident, that the laws permitting life and consciousness are not random outcomes, but expressions of a principle or purpose or pattern that reaches from the quantum foam to the largest structures in the cosmos, if that we, improbable and temporary as we are, stand at the intersection of matter and meaning, asking questions that the universe itself seems structured to provoke. The problem begins with a question that feels almost too simple to ask. What if the numbers were different? Not the numbers we invent to count stars or measure distances, but the numbers woven into the fabric of existence itself, the fundamental constants that govern how particles interact, how forces propagate, how space expands and matter clumps and energy flows across the void. There are roughly 24 such constants, values that cannot be predicted from theory but must be measured from the universe as it is, then inserted into equations like fixed parameters in a cosmic operating system. The speed of light, the gravitational constant, the masses of the electron and the quarks, the strengths of the four fundamental forces, these are not derived from deeper principles, at least not yet, but simply given brute facts of nature that physics accepts because observation demands it. And when you examine these constants closely, when you ask what would happen if they shifted even slightly from their observed values, the answer that emerges is both simple and terrifying. The universe would collapse into sterility, a place where stars never ignite, atoms never form, chemistry never begins. When the long road from hydrogen to consciousness never finds its first step. Consider gravity, that weakest of the four forces, so feeble that a child's magnet can overpower the entire planet's gravitational pull on a paperclip, yet so precisely calibrated that if it were stronger by even a modest factor, stars would burn through their nuclear fuel in mere millions of years instead of billions. Their lifespans too brief for planets to cool and oceans to stabilize and life to crawl from the chemistry of primordial seas. If gravity were weaker by a comparable margin, matter would fail to clump together into dense enough clouds to ignite fusion, leaving the universe filled with cold gas, drifting forever through an ever-expanding dark. No heat, no light, no stellar forges to transmute hydrogen into the heavier elements that build rocky worlds and organic molecules. The balance is not approximate, but exact within a narrow window. And astronomers who study stellar evolution can trace this window's edges by modeling how stars of different masses burn their fuel, how their cores collapse and their outer layers explode, and how those explosions seed the interstellar medium with carbon, oxygen, nitrogen, iron, the alphabet of complexity. Alter gravity by a factor of just a few, and all stars become either red dwarfs too dim and unstable to host habitable planets, and blue giants that blaze furiously and die young, never lingering long enough for planets to form, let alone for evolution to build nervous systems capable of looking up and wondering why the sky is filled with stars. But gravity is only one thread in the fine-tuned tapestry. The strong nuclear force, which binds quarks into protons and neutrons and holds those nucleons together inside atomic nuclei against the electromagnetic repulsion of their positive charges, tolerates a variation of just 2% before the universe becomes unrecognizable. If the strong force were 2% weaker, nuclei with more than one proton would never hold together, and the periodic table would collapse into a single-entry list. Hydrogen, and nothing else. No carbon, no oxygen, no iron, no silicon, no chemistry beyond the simplest molecule, water impossible, proteins unthinkable, DNA a fantasy that could never be encoded into reality. If the strong force were 2% stronger, the opposite catastrophe unfolds. Hydrogen would fuse into helium and heavier elements with such efficiency that within moments of the Big Bang, all the hydrogen in the universe would be consumed, leaving no fuel for stars, no protons to form water, no long-burning suns to warm the surfaces of worlds where liquid might persist long enough for chemistry to become biology. The margin is not generous, not a broad range where different outcomes still permit structure and complexity, but a knife edge where a shift of 1 part in 50 in either direction erases the possibility of a cosmos that looks anything like ours. Yet the truth may be stranger than these individual constraints suggest. But the constants do not act in isolation, but in concert, their values interlocking in ways that amplify the fragility of the life-permitting regime. The electromagnetic force, quantified by the fine structure constant alpha, approximately 1 divided by 137, determines the strength of interactions between charged particles and the structure of atoms, how tightly electrons orbit nuclei, how much energy photons carry, how stable chemical bonds form. If alpha were 4% larger, the resonance level in the carbon nucleus that allows helium nuclei to fuse into carbon in stellar cores would shift out of alignment, and carbon production would plummet, cutting off the pathway to organic chemistry and silicate geology, leaving a universe where the only abundant elements are hydrogen and helium, too simple to build complexity, too light to form solid worlds. A similar calculation shows that if alpha were slightly smaller, oxygen production would drop catastrophically. And without oxygen, there is no water, no atmosphere capable of supporting aerobic life, no oxidation reactions to release energy from organic molecules, no rust to weather rock into soil. The window is narrow, measured in single-digit percentages, and within that window lies the possibility of a universe rich enough in chemical diversity to support the emergence of replicators, metabolisms, ecosystems, minds. And this is where the vertigo begins. And the fragility of these parameters is not limited to forces and particles, but extends to the initial conditions of the universe itself, to the distribution of matter and energy in the first fractions of a second. And quantum fluctuations in the inflationary epoch seeded the density variations that would later grow into galaxies, clusters, and the cosmic web. If the early universe had been slightly smoother, if those fluctuations had been smaller by even a modest factor, gravity would never have amplified them into the regions of overdensity necessary to collapse into stars and galaxies. If the cosmos would remain a featureless expanse of thinly spread gas, cooling forever, structureless, and lifeless. If the fluctuations had been slightly larger, the overdense regions would have collapsed not into galaxies, but into black holes. And the universe would be dominated by these gravitational traps, swallowing matter and light before stars could ignite or planets could form. The spectrum of fluctuations observed in the cosmic microwave background, the oldest light in the universe, fits within a narrow band that cosmologists can quantify with precision, and that band corresponds to the only range of initial conditions capable of producing a universe where structure emerges gradually, hierarchically, building complexity over billions of years. Here a question emerges that even skeptical physicists find difficult to dismiss. How improbable is this? If the constants could have taken any value across a wide range, if there is no deeper principle constraining them to their observed values, if the probability that they would all land within the narrow windows necessary for stars, chemistry, if life becomes not merely small but vanishingly tiny, a lottery with odds so staggering that invoking luck feels less like an explanation and more like an evasion. The cosmological constant, that measure of dark energy's density expressed in Planck units, sits at a value of roughly 10 to the negative 122nd power, a number so small that quantum field theory predicts it should be 50 or even 120 orders of magnitude larger. Yet if it were even slightly larger than its observed value, space would have expanded so rapidly that matter could never clump into galaxies, and if it were smaller or negative, the universe would have recollapsed into a big crunch long before the first stars could light the void. This discrepancy between what theory predicts and what observation requires has been called the worst fine-tuning problem in physics, not because the theory is wrong, but because explaining why the cosmological constant takes the value it does seems to require a cancellation so precise, so improbable, that it strains credulity to attribute it to chance. But there is a deeper problem lurking beneath the surface of these calculations, because fine-tuning is not merely about individual constants falling within narrow ranges, but about the relationships between them, the way that changes in one parameter can be compensated by adjustments in another, creating a high-dimensional landscape where the life-permitting region is not a single point but a complex, convoluted volume whose shape we are only beginning to map. Some physicists have explored this landscape by running computer simulations of universes with different constants, tweaking the strength of gravity or the mass of the electron or the cosmological constant, and watching how stars form or fail to form, how galaxies collapse or disperse, how chemistry becomes possible or impossible. The results are both reassuring and unsettling. While it is true that many combinations of constants lead to lifeless universes, there are also parameter spaces where the universe becomes more life-friendly than our own, producing more stars, more heavy elements, more habitable zones around longer-lived suns, suggesting that fine-tuning is not about finding the single unique set of values that permits life, but about navigating a narrow ridge in a vast landscape where most directions lead to sterility, but some lead to even greater fecundity. This realization complicates the narrative, because if our universe is not the most life-friendly possible universe, because the appearance of fine-tuning may not be evidence of design, but evidence of something else, a selection effect, or a statistical inevitability, or a deeper law that constrains the constants in ways we do not yet understand. Yet the numbers themselves resist comfortable explanations, because even physicists who approach the fine-tuning problem with skepticism find themselves confronting the eerie precision of the cosmic parameters. The ratio of the electron's mass to the proton's mass, approximately 1 to 1836, determines the stability of atoms, the strength of chemical bonds, the size of molecules. And if this ratio were even slightly different, the chemistry of life would become impossible, either because atoms would be too unstable to persist, or because bonds would be too weak to hold molecules together against thermal fluctuations. The weak nuclear force, responsible for radioactive decay and the fusion processes in the Sun, must be tuned within a factor of 10 or so to avoid catastrophic outcomes. Weaker, and neutrons would fail to decay into protons in the early universe, leading to a rapid conversion of all hydrogen into helium and heavier elements, leaving no long-term fuel for stars, stronger. And the fusion chain in stellar cores would be disrupted, altering the balance between hydrogen burning and helium production in ways that prevent the formation of stable, long-lived stars like the Sun. Each constant seems to know about the others, their values fitting together like pieces of a puzzle whose final image is a universe capable of supporting complexity, awareness, and the capacity to ask why the puzzle fits together at all. And this is where the story bends toward paradox. And the fine-tuning problem is not just about the improbability of the constants, but about the meaning of that improbability, about whether it points toward design, necessity, and selection, and whether any of those explanations can satisfy both our mathematical rigor and our philosophical unease. Some physicists argue that the constants are not arbitrary but necessary, that a more complete theory, perhaps a theory of quantum gravity or a unified framework that merges all forces into a single mathematical structure, will reveal that the constants we measure are not independent dials, but emergent properties of deeper laws, constrained by symmetries or principles we have not yet discovered, reducing the apparent fine-tuning to an inevitable consequence of how reality must be. This is an appealing possibility, because it replaces the mystery of coincidence with the elegance of necessity, suggesting that the universe could not have been otherwise, that the constants take the values they do because those are the only values consistent with a self-consistent mathematical framework. Yet this explanation merely relocates the question rather than answering it, because even if the constants are determined by deeper laws, we are still left to wonder why those deeper laws should exist, why they should take the form they do, because why they should be the kind of laws that permit stars, chemistry. Because conscious beings capable of uncovering the laws themselves. Others propose a different resolution, invoking the multiverse, an infinity of parallel universes where every possible combination of constants plays out, most of them sterile and lifeless, because some, like ours, falling within the narrow life-permitting windows simply because, given enough trials, even improbable outcomes become inevitable. In this view, the fine-tuning of our universe is not evidence of design, but evidence of selection. We observe a life-friendly universe not because it was tuned for life, but because we could only exist in a universe where the constants permit our existence. And all the lifeless universes go unobserved because there is no one in them to observe. The multiverse hypothesis is mathematically seductive, arising naturally from some versions of inflationary cosmology and string theory, frameworks that suggest the early universe underwent a brief but violent expansion that could have spawned countless bubble universes, each with its own set of constants determined by the way quantum fields settled into their lowest energy states. Yet this explanation, while dissolving the fine-tuning problem in one sense, introduces its own mysteries. If the multiverse is real, what determines the distribution of constants across those infinite realms? While does that distribution itself require fine-tuning to ensure that at least some universes fall within life-permitting ranges, while is the distribution so broad that life-permitting universes are vanishingly rare, making our existence a kind of cosmic miracle even within the multiverse framework? The tension grows as even skeptical physicists, those trained to resist teleological explanations and to seek natural, law-based accounts of phenomena, Admit that the numbers feel suspiciously perfect, that the alignment of forces and masses and expansion rates seems less like random chance and more like a blueprint. While if the universe were following an invisible template whose purpose remains opaque. The physicist Fred Hoyle, upon discovering the carbon resonance level that allows helium to fuse into carbon in stellar cores, famously remarked that the level seemed so precisely tuned that he could not shake the feeling that the universe had been deliberately set up to produce carbon and the chemistry that depends on it. This was not a religious sentiment, but an empirical observation, a recognition that the data pointed toward a degree of precision that resisted comfortable naturalistic explanations. And Hoyle's unease has been echoed by other physicists who have studied the fine-tuning problem and found themselves confronting the limits of what coincidence or necessity or selection can plausibly explain. What we know is this: the universe exists on a razor-thin boundary between existence and sterility, and the margin by which it avoids catastrophe is so narrow that even small deviations in fundamental constants would erase stars, collapse chemistry, and prevent galaxies from forming. What we do not know is whether this boundary is evidence of intention, whether it reflects a deeper order we have not yet understood, or whether it is merely the selection effect of a multiverse so vast that even the most improbable configurations must occur somewhere. The fragile cosmic parameters do not announce their origin, do not come with labels explaining whether they were chosen, derived, or randomly sampled from a distribution of possibilities. Or the universe offers no clear answer to the question of why the numbers that govern its behavior should be precisely the numbers necessary to permit complexity, awareness, or the capacity to decode the universe's own structure. Yet the question persists, quiet but insistent, woven into the equations of stellar physics and the observations of cosmic structure. Is the universe fine-tuned for life? Or is life an emergent byproduct of fine-tuned physics? If the former, then the constants are the expression of a purpose or principle that transcends the physical laws themselves, suggesting that the universe was designed or constrained or selected in such a way that conscious beings capable of understanding would eventually arise. If the latter, then life is not the goal but the consequence, a pattern that emerges inevitably when matter and energy interact under the right conditions. Then the fine-tuning we observe is not evidence of design, but evidence that complexity requires specific physical parameters, that there is no other way to build stars and planets and organic chemistry without the constants falling within the narrow windows we measure. Perhaps the truth lies somewhere between these poles, in a universe where the distinction between design and emergence dissolves, where the laws of physics are such that structure and consciousness arise not as accidents, but as natural expressions of the way reality organizes itself when given the right initial conditions and enough time. The fine-tuned blueprint, where it is a blueprint, does not reveal its author. Where the universe remains silent on the question of whether its eerie precision is the signature of intention or the inevitable outcome of a deeper mathematics we have not yet uncovered. What we can say is that the constants are fragile, that the life-permitting windows are narrow, and that our existence depends on a delicate balance of forces and masses and expansion rates whose origin remains one of the deepest mysteries in science, a mystery that touches not only on the physics of stars and galaxies, but on the nature of existence itself, on why there is something rather than nothing, and why that something should be structured in such a way that beings like us can emerge from hydrogen and starlight, and ask why the universe permits us to exist at all. There is a moment when you stare long enough at the equations that govern particles and forces, when the symbols begin to lose their grip on the physical and reveal something stranger underneath, not matter or energy or even space-time, when pattern, structure, relationship, when if the universe were less a collection of things and more a web of rules performing themselves into existence. The laws of physics do not merely describe how reality behaves. They seem to constitute reality, to the point where asking which comes first, the mathematics or the matter, feels less like a philosophical curiosity and more like a question the universe is actively posing to anyone willing to listen closely enough. Symmetry groups, those abstract collections of transformations that leave certain properties unchanged, dictate which particles can exist and which forces can act, as if the particle zoo of quarks and leptons and bosons were not fundamental entities, but shadows cast by deeper geometric principles, excitations in fields that ripple through space-time according to equations so elegant they feel less discovered than inevitable. Quantum fields, those invisible substrates permeating the vacuum, behave like information processors, encoding states in superpositions and entanglements, transforming inputs into outputs through unitary operations that preserve information even as they scramble it beyond recognition. And the particles we observe, the electrons, photons, and quarks, are not objects in the classical sense, but localized patterns of excitation, vibrations in these fields whose properties emerge from the symmetries, and conservation laws that constrain how information can flow through the quantum fabric. Pythagoras glimpsed this truth 25 centuries ago when he declared that all is number, that the harmony of the cosmos arises from ratios and proportions, from the intervals between musical notes and the orbits of planets, a vision dismissed as mysticism until physicists began to realize that the fundamental constants, the masses and charges and coupling strengths, are indeed numbers, dimensionless ratios that determine how reality unfolds, and that these numbers seem chosen not arbitrarily, but according to some hidden criterion of mathematical coherence. Plato took the idea further, proposing that the visible world is a shadow of eternal forms, perfect geometric structures existing outside time and space. And while his theory of forms has long been relegated to philosophy seminars, the discovery that particles obey representations of Lie groups, that spacetime curvature follows from the metric tensor, that quantum states live in Hilbert spaces whose dimensions correspond to degrees of freedom, suggests that Plato was not entirely wrong. There is a realm of pure mathematics, and the physical universe appears to be its implementation, its runtime, its instantiation in something we call matter and energy, but which may be nothing more than the output of abstract rules operating on themselves. Einstein completed the picture by showing that spacetime itself is not a stage on which events occur, but a dynamic entity shaped by the distribution of matter and energy, bending and warping according to equations whose left side describes geometry and whose right side describes mass, and the equality sign between them is not a mere convenience, but a statement that geometry is matter, that the curvature of space is indistinguishable from the presence of mass, collapsing the distinction between the arena and the actors, between the code and the execution. But the deeper we search for the source of these patterns, the more abstract the code becomes, dissolving from particles into fields, from fields into operators, from operators into symmetries, from symmetries into mathematical structures so detached from sensory experience that even physicists trained in the formalism struggle to say what and anything these structures correspond to in a reality independent of our descriptions. Quantum mechanics, the theory that governs the microscopic realm, does not predict outcomes but amplitudes, complex numbers whose squared magnitudes give probabilities, and these amplitudes evolve according to a wave equation whose solutions are not waves of matter or waves of energy, but waves of information, distributions of potential encoded in a mathematical object called a state vector that lives in an abstract space where the axes represent not spatial directions, but possible measurement. Results. When you measure a quantum system, you do not merely observe a pre-existing property, but collapse the wave function, forcing the system to choose a definite state from among the superposition of possibilities it inhabited before observation. And this collapse is not a physical process in the usual sense. There is no known mechanism, no force or interaction that triggers it, but rather an informational update, a recalibration of what can be said about the system given the measurement result. And if reality itself is less concerned with being in specific states and more concerned with maintaining consistency between what different observers can infer from their measurements. Yet the truth may be stranger than even this formulation suggests, and quantum field theory, the framework that extends quantum mechanics to relativistic speeds and allows particles to be created and destroyed, treats the vacuum not as empty space, but as a roiling sea of virtual particles, fleeting fluctuations that borrow energy from the future and pay it back so quickly that the uncertainty principle permits their brief existence. And these fluctuations are not mere theoretical conveniences, but have measurable consequences. They shift the energy levels of atoms, generate forces between uncharged plates in vacuum, and contribute to the cosmological constant that drives the universe's accelerated expansion. The vacuum, then, is not nothing but a state of maximum symmetry, a configuration where all quantum fields sit at their lowest energy. Yet even this lowest state contains infinite potential, a substrate from which particles can be excited like ripples on a pond. And the distinction between particle and vacuum becomes blurred, contingent on how you partition energy, how you define what counts as something versus nothing. The particles themselves, those entities we think of as the building blocks of matter, are revealed by quantum field theory to be not fundamental objects, but quanta, discrete units of excitation in fields that extend across all of space. And when an electron moves from one place to another, it is not a tiny sphere traveling through the void, but a ripple in the electron field, a localized disturbance whose motion is governed by the field's equations. And the field is not made of anything. It is a mathematical entity, a function that assigns a value to every point in spacetime, and those values evolve according to rules derived from symmetry principles and conservation laws. Here a question emerges that unsettles even those comfortable with quantum abstraction. Are particles real, and are they just excitations in a deeper informational medium, patterns of data encoded in a substrate we cannot directly access? The holographic principle, emerging from black hole thermodynamics and string theory, suggests that the information content of a region of space is proportional not to its volume, but to the area of its boundary, as if the three-dimensional reality we experience is a projection from a two-dimensional surface, a hologram encoding all the data necessary to reconstruct what appears to be a volumetric universe. This principle is not metaphorical but mathematical, arising from the realization that black holes have entropy proportional to their surface area, and that entropy measures information, the number of microstates consistent with a given macroscopic configuration, implying that the maximum information that can be contained in a region scales with its boundary rather than its interior, a scaling that makes no sense if information is a property of three-dimensional matter but makes perfect sense if the matter itself is emergent, a higher-dimensional representation of information encoded on a lower-dimensional substrate. And this is where the story bends toward vertigo. And if reality is code, and the laws of physics are algorithms and particles are data structures, and spacetime is the output of a computational process running on some unknown hardware. And the question shifts from what the universe is made of to what system is running it, what substrate supports the computation, and whether that substrate is itself physical or something more fundamental, more abstract, perhaps even something outside the framework of space and time altogether. John Archibald Wheeler, one of the architects of modern physics, proposed that information is the foundation of reality, coining the phrase "it from bit" to capture the idea that every physical quantity, every particle, every field, ultimately derives from binary choices, yes or no questions whose answers accumulate into the rich structure we perceive as the material world. In Wheeler's view, the universe is not a machine made of matter but a self-interrogating system, a network of measurements and observations that bootstrap themselves into existence, where observers are not external to reality but integral to it, where the act of asking a question, of performing a measurement, brings into being the answer, where the collective result of all such measurements is what we call the physical universe. Yet the eeriness of mathematical inevitability persists, the unsettling observation that the universe follows elegant equations instead of chaotic ones, that the laws governing particle interactions can be derived from variational principles that minimize action, that symmetries constrain dynamics, that conservation laws emerge from invariances under transformations, where if the cosmos were optimizing itself according to some criterion of simplicity or beauty or efficiency that we can recognize but not explain. The standard model of particle physics, which describes 3 of the 4 fundamental forces and catalogs all known elementary particles, is built on the gauge symmetries of the groups U1, SU2, and SU3, abstract mathematical structures that dictate which interactions are allowed and which are forbidden, and the success of this model, its ability to predict experimental results to absurd precision, its explanation of phenomena from the hydrogen spectrum to the behavior of quarks inside protons, rests entirely on the assumption that these symmetries are fundamental, that they are not approximations or conveniences, but the deep logic from which physical law emerges. The Higgs mechanism, which explains how particles acquire mass, is a consequence of spontaneous symmetry breaking, a process where the underlying laws remain symmetric but the vacuum state does not, choosing a particular configuration from among many equivalent possibilities. And this choice ripples outward, giving mass to the W and Z bosons while leaving the photon massless, a delicate balance that permits atoms to form, chemistry to develop, and complex structures to arise. But there is a deeper problem, lurking beneath the elegance of these equations, and the symmetries themselves are not derived from anything more fundamental. They are postulated, chosen because they work. And they fit the data. Yet the question of why these symmetries and not others, why SU3 for the strong force and not SU4 or SO5, remains unanswered, and the constants that appear in these equations, the coupling strengths, the masses, the mixing angles, are free parameters, numbers that must be measured from nature rather than calculated from theory, suggesting that the code, and elegant, is incomplete, that there is a deeper layer of logic we have not yet accessed. String theory, which posits that particles are not point-like objects but tiny vibrating loops of energy, offers a candidate for this deeper layer, proposing that all particles and forces arise from different vibrational modes of these strings, that the equations of the Standard Model are approximations valid at low energies, and that a more complete description requires extra dimensions, hidden from view by being curled up into spaces too small to detect, and in these extra dimensions the strings vibrate in patterns that correspond to the particles and forces we observe, encoding the laws of physics in the geometry of spacetime itself. Yet string theory, for all its mathematical beauty, has not yet made contact with experiment, has not predicted new phenomena that distinguish it from alternative frameworks, and the landscape of possible string vacua, different ways the extra dimensions can be configured, is vast, perhaps infinite, raising the possibility that our universe is one configuration among countless others, each with its own laws, its own particles, its own constants, turning the question of why our universe has the laws it does into a question of selection rather than derivation. Yet the idea that reality might not be physical at all, that matter and energy are emergent properties of relationships, logic, and information, is not merely speculative philosophy, but is grounded in the formalism of quantum mechanics and the structure of quantum field theory. And observables are represented by operators, states by vectors, and dynamics by unitary transformations, and none of these objects are tangible in the way we think of tables and chairs and planets as tangible. They are mathematical entities whose physical interpretation depends on the context of measurement, on the choice of basis, on the way we partition the system from its environment. Entanglement, the phenomenon where quantum systems become correlated in ways that cannot be explained by any local hidden variables, where measuring one particle instantaneously affects the state of another regardless of the distance separating them, violates the classical notion that objects have independent existence, suggesting instead that the fundamental entities of quantum theory are not particles but correlations, not things but relationships, not localized bits of matter but distributed patterns of information that only collapse into definite, localized states when observed. The no-cloning theorem, which proves that it is impossible to create an identical copy of an arbitrary, unknown quantum state. And the no-hiding theorem, which shows that quantum information cannot be destroyed but only relocated or scrambled, both follow from the unitarity of quantum evolution, from the requirement that information is conserved, and these theorems place constraints on what the universe can do, on what processes are physically realizable, and if the cosmos itself is subject to informational laws that transcend the specific details of particles and forces. And this is where the cliffhanger takes shape. And if the universe is code, and reality is computation, and particles are data, and spacetime is the output. And the next question is unavoidable. What, or who, runs it? Is there a substrate beneath the quantum fields, a hardware layer on which the code executes? Or does the code execute itself? bootstrapping reality into existence through some self-referential loop where the laws of physics create the conditions necessary for those laws to apply. The simulation hypothesis, popularized by philosophers and physicists alike, proposes that our universe might be a computational construct running on some vastly powerful computer in a higher-level reality, that the laws of physics are the software governing this simulation, and that we, and conscious beings within this simulation, have no access to the underlying hardware or the entities that programmed it. This idea is less outlandish than it sounds, because we already know that finite computational resources can generate convincing simulations of complex systems, that video games can create immersive worlds with their own internal rules, because that if computational power continues to grow, it may one day be possible to simulate entire universes with conscious observers who believe themselves to be real. Because if such simulations are possible, because the number of simulated universes could vastly exceed the number of real ones, leading to the conclusion that we are statistically more likely to be living in a simulation than in the base reality. Yet the truth may be stranger, because simpler. Because both. Because the question of who runs the code presupposes that there is a who, an external agent or programmer, because the universe might instead be self-organizing, its laws emerging from consistency conditions, from the requirement that information be conserved, that causality be respected, that symmetries not be violated. Because these requirements alone might be sufficient to generate the structure we observe, without need for a designer or a substrate or a higher-level reality in which the code executes. In this view, the universe is not running on anything but is the running itself, a process that unfolds according to its own internal logic, where the distinction between the code and the execution collapses. Where asking what hardware supports the computation is like asking what supports mathematics. It is a category error, a confusion of levels, where mathematics does not exist in space or time, but is the structure from which space and time emerge. The historical arc of physics, from Newton's mechanical universe to Maxwell's electromagnetic fields to Einstein's curved spacetime to the quantum realm of superpositions and entanglements, has been a progressive abstraction, a movement away from concrete objects and toward relationships, symmetries, where informational constraints. Newton imagined particles as tiny billiard balls, localized objects with definite positions and velocities, interacting through forces that propagate instantaneously across space. Maxwell replaced this with fields, continuous entities that permeate the vacuum and carry energy and momentum, and showed that light itself is a wave in the electromagnetic field. Einstein unified space and time into a single geometric structure, showed that mass curves this structure and that curvature tells mass how to move, dissolving the distinction between the stage and the play. Quantum mechanics went further, replacing deterministic trajectories with probability amplitudes, showing that particles do not have definite properties until measured, that observation is not passive but active, that the observer and the observed are entangled in ways that cannot be disentangled without fundamentally altering the system. And now, at the frontier of theoretical physics, the trend continues. Quantum field theory treats particles as excitations in fields. String theory treats fields as emergent properties of vibrating strings. Loop quantum gravity treats spacetime itself as quantized, made of discrete units called spin networks. And the holographic principle suggests that all of this, particles, fields, strings, spacetime, is a projection from information encoded on a boundary. The question, then, is not whether the universe is code but what kind of code it is, whether it is a program with an input and an output, running on hardware in some external reality, and whether it is more like mathematics itself, a self-consistent structure that exists necessarily, not because it was created, but because its internal logic leaves no other option. The physicist Max Tegmark has proposed that the universe is mathematics, not merely described by mathematics, but identical to it. That physical reality is a mathematical structure, and we are patterns within that structure, experiencing it from the inside. And that the reason mathematics is so unreasonably effective at describing the universe is that there is no distinction to draw. Mathematics is reality, and reality is mathematics. And the laws of physics are theorems in a vast axiomatic system whose axioms we are still trying to uncover. This view dissolves the mystery of why the universe follows elegant equations. It follows them because it is them, because there is no universe apart from the equations, no matter separate from the mathematics that defines its behavior. Yet even this dissolution leaves a residue of mystery, because if the universe is mathematics, because why this mathematics and not another? Why the axioms that give rise to quantum fields and curved spacetime, and not some other set of axioms that would produce a universe with different laws, different constants, different structures? And if all mathematical structures exist in some Platonic realm of abstract forms, then why do we find ourselves in this particular one, experiencing this particular instantiation of mathematical necessity? The anthropic principle offers one answer. We could only exist in a universe whose mathematics permits complexity and consciousness, and so the fact that we find ourselves in such a universe is not surprising, not evidence of design, and a selection effect, a tautology dressed up as an explanation. But this answer feels incomplete, unsatisfying, because it replaces the question of why the universe has the structure it does with the question of why we are here to observe it, because the latter question is no less mysterious than the former, perhaps more so. Because it introduces consciousness into the equation, because consciousness is the one phenomenon that resists reduction to mathematics, the one aspect of reality that seems irreducibly subjective, irreducibly experiential, irreducibly tied to the first-person perspective that no amount of equations can capture. The hidden codes of physics, because they are codes, do not announce their origin or their purpose. Because the universe remains silent on the question of whether its mathematical structure is the work of a programmer, the output of a self-organizing process, because the inevitable expression of logical necessity operating on itself. What we can say is that the laws of physics are extraordinarily constrained, that symmetries and conservation principles and the requirement of mathematical consistency narrow the space of possible laws to a small subset of what we might imagine, and that this subset is precisely the one that permits complexity, structure, and the emergence of beings capable of decoding the mathematics that governs their own existence. Whether this is coincidence, design, or necessity remains an open question, or the trend of physics is clear. The deeper we probe, the more abstract the foundations become, or we are left not with objects or substances, but with patterns and relationships and informational constraints. Or the question of what, or anything. These patterns are patterns of dissolves into the question of whether the patterns need to be patterns of anything at all, or whether the patterns themselves, the relationships, the logic, the information, are all that reality is, all that it ever was, all that it ever could be. There is a way out of the fine-tuning problem that requires no designer, no intention, no cosmic architect standing outside reality and calibrating constants, but it demands something stranger, something more vertiginous, the possibility that our universe, with all its eerie precision and life-permitting parameters, is not unique but one outcome among countless others. A single bubble in an infinite foam of universes where every possible combination of laws, constants, and initial conditions plays out somewhere, and we find ourselves here not because this universe was designed for us, but because only universes like this one can produce beings capable of noticing they exist. The multiverse hypothesis, in its various forms, proposes that beyond the observable cosmos, that sphere of space roughly 90 billion light-years across containing everything our telescopes can detect, there exist other universes, possibly infinite in number, each with its own configuration of physical laws, its own values for the fundamental constants, its own history stretching from its own beginning to its own fate. These universes may be disconnected from ours, separated by barriers of space or time or dimensionality that render them forever inaccessible, or they may be connected in subtle ways, influencing each other through gravitational effects or quantum entanglements or collisions that leave faint imprints on the cosmic microwave background, bruises in the fabric of spacetime that careful observation might one day detect. Cosmic inflation, the theory that the early universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang, provides one pathway to the multiverse, or the mechanism that drives inflation. A field permeating space whose energy density remains nearly constant even as space expands, does not necessarily turn off everywhere at once. In some regions, inflation ends and space settles into a lower energy state, cooling into a universe like ours where matter condenses and galaxies form and stars ignite. In other regions, inflation continues, driving further expansion, and within that expanding space, new regions can undergo their own transitions, spawning new universes in a process that never ends. An eternal inflation that populates the multiverse with bubble universes, each one a pocket of space where inflation has ceased, and physics as we know it can begin. The mathematics of eternal inflation is well developed, arising naturally from the equations governing scalar fields in curved spacetime, and the predictions of inflation, the flatness of space, the spectrum of density fluctuations, the uniformity of the cosmic microwave background, match observations with striking precision, lending credibility to the inflationary framework and, by extension, to the multiverse it generates. Yet the bubble universes produced by eternal inflation need not have identical laws. Quantum fluctuations during the inflationary epoch can cause different regions to settle into different vacuum states. And if those vacuum states correspond to different configurations of fields and forces, and each bubble universe may have its own physics, its own values for the constants that govern particle masses and interaction strengths, its own cosmological constant determining the rate at which space expands. String theory, that framework which posits that particles are not point-like objects but tiny vibrating loops of energy, whose vibrational modes correspond to different particles and forces, offers another route to the multiverse through what is called the landscape, a vast space of possible vacuum configurations arising from the many ways that extra-spatial dimensions beyond the three we experience, can be compactified, curled up into shapes too small to detect. Each point in this landscape corresponds to a different vacuum state, a different low-energy configuration of the fields that permeate spacetime. And each such configuration gives rise to a universe with its own set of physical laws and constants, its own particles and forces, its own cosmological constant. The number of possible configurations in the string landscape is staggering, estimated to be on the order of 10 to the 500th power or more, a number so large that it dwarfs any human intuition for scale. And if eternal inflation populates this landscape by allowing different regions of space to settle into different vacua, and the multiverse becomes not merely infinite in extent, but infinite in diversity, containing universes with every conceivable arrangement of laws and constants that the landscape permits. In this framework, the fine-tuning of our universe is not a puzzle demanding explanation, but a statistical inevitability. With so many universes, each with different parameters, some fraction of them will have constants that fall within the narrow life-permitting windows. And we necessarily find ourselves in one of those rare universes because only they can produce observers capable of asking why the constants have the values they do. Yet there is a deeper disquiet lurking in this explanation. And the multiverse removes the need for intention only by introducing the overwhelming scale of infinite possibilities. A landscape so vast that every conceivable universe exists somewhere, including universes where the constants are slightly different, and life arises in forms utterly alien to our chemistry, and stars burn blue or red or not at all, and galaxies collapse into black holes or disperse into emptiness, and the laws of physics permit complexity or forbid it, and we are left to confront the vertigo of existence as a cosmic lottery. Our presence here not the result of purpose or design, but the inevitable outcome of playing the game enough times that even the most improbable results must occur. The anthropic principle, which states that we can only observe a universe compatible with our existence, takes on a new dimension in the multiverse framework. It is no longer a tautology, but a selection effect, a filter that constrains which universes we could ever find ourselves in. And the fine-tuning we observe is not evidence of engineering, but evidence that we are sampling from a biased subset of the multiverse, the rare pockets where the constants permit complexity and consciousness. This is intellectually satisfying in one sense, because it dissolves the mystery of fine-tuning without invoking anything supernatural or transcendent. because it is unsettling in another, because it suggests that our universe, with all its galaxies and stars and planets, and the entire history of life on Earth, is an accident, a random draw from an infinite deck of possibilities, no more meaningful than any other configuration of matter and energy that happens to arise in the vast expanse of the multiverse. But there is a deeper problem, one that critics of the multiverse hypothesis seize upon with some justification. There is no direct evidence for other universes, no way to observe them or measure their properties or test the predictions of multiverse theories in the same way we test other scientific hypotheses. The observable universe, that sphere of space from which light has had time to reach us since the Big Bang, is all we can access with telescopes and detectors, and everything beyond that horizon is, by definition, unobservable, forever hidden from direct measurement. The multiverse, in most of its formulations, lies beyond this horizon, existing in regions of space or configurations of dimensions that we cannot probe. And while the theories that predict the multiverse, inflation, string theory, quantum mechanics, have other testable consequences, the multiverse itself remains a theoretical construct, inferred from the mathematics of those theories, but not directly confirmed by observation. This has led some physicists to argue that the multiverse is not science but metaphysics, a philosophical speculation dressed up in the language of equations, unfalsifiable in principle, because any observation we make, any measurement we perform, will necessarily be confined to our own universe and cannot tell us whether other universes exist. Yet the truth may be more nuanced, because while the multiverse as a whole may be unobservable, specific versions of the multiverse hypothesis make predictions that could, in principle, be tested. Because some of those predictions have already been ruled out or constrained by observation. The inflationary multiverse, for instance, predicts that if bubble universes collide, the collision could leave a detectable imprint on the cosmic microwave background, a circular pattern of temperature fluctuations that careful analysis might reveal, and astronomers have searched for such signatures without finding convincing evidence. And the absence of evidence is not evidence of absence. It could simply mean that our observable universe has not been involved in a recent collision, and that the collisions are too subtle to detect with current instruments. The string landscape multiverse makes predictions about the distribution of constants across the ensemble of universes. And while we cannot measure those constants in other universes, we can ask whether the constants in our universe are typical or atypical within the distribution that string theory predicts, and this question, and fraught with statistical subtleties, offers a way to test whether the multiverse framework is consistent with the values we observe. The quantum multiverse, arising from the many-worlds interpretation of quantum mechanics, proposes that every quantum measurement splits the universe into branches corresponding to different outcomes, and while these branches cannot communicate with each other, decoherence ensures they remain isolated. The interpretation makes predictions about the probabilities of different outcomes that can be compared with experiment, and some physicists argue that the many-worlds interpretation is the most straightforward reading of the quantum formalism, requiring no additional assumptions beyond the Schrödinger equation itself. And this is where the story bends toward loneliness. And if the multiverse is real, and countless universes exist with different laws and constants, and the question of whether we are alone in the cosmos takes on a new dimension, not just whether life exists elsewhere in our universe, and whether consciousness arises in other universes, whether beings in those universes experience reality in ways we cannot imagine, whether the structure of their thoughts and perceptions is constrained by the same logic that governs ours, or whether different laws of physics permit different forms of awareness, different kinds of minds. The loneliness is not physical but existential. The realization that if the multiverse is infinite and diverse, then every possible configuration of matter and energy exists somewhere, including universes where consciousness never arises. Then stars burn but no one sees them. Then galaxies form but no one contemplates their origin. Then the universe we inhabit, teeming with structure and complexity and the fragile spark of awareness, is one island of meaning in an ocean of meaningless alternatives. Then the vast majority of universes, by sheer statistical weight, are sterile, lifeless, empty. Yet the dread of meaning dissolving into randomness is not the only response to the multiverse hypothesis. Then there is another way to interpret the ensemble of universes, not as a collection of disconnected accidents, but as a grander cosmic ecology, a system where different universes play different roles. Then the diversity of laws and constants is not a bug, but a feature. Then the multiverse as a whole exhibits structure and organization that transcends the individual universes it contains. This idea is speculative, more philosophy than physics, but it offers a counterpoint to the nihilistic reading of the multiverse, suggesting that if countless universes exist, but the multiverse itself might be the fundamental reality, but our universe is one expression of that reality, one way that the underlying principles manifest. But the question of why this universe exists shifts to the question of why the multiverse exists, why there should be anything at all rather than nothing. But whether the multiverse itself is necessary, eternal, self-organizing, but contingent on something deeper still. The criticisms of the multiverse hypothesis are not trivial, but even proponents acknowledge that the framework raises as many questions as it answers. If the multiverse is real, then what determines the distribution of universes across the landscape of possibilities? Then is that distribution itself fine-tuned, requiring explanation in the same way that the constants in our universe require explanation? If inflation is eternal, populating the multiverse with bubble universes forever, then does the process have a beginning? Then if so, what initiated it? Then if not, how can an infinite past be reconciled with the thermodynamic arrow of time that points toward increasing entropy? If the many-worlds interpretation of quantum mechanics is correct, splitting the universe into branches with every measurement, then how do we define probability in a framework where all outcomes occur? Then what does it mean to say that one outcome is more likely than another if both actually happen in different branches? These are not easy questions, and the answers, and they exist, lie at the frontiers of theoretical physics, and mathematics and philosophy blur into each other, and where the demand for empirical evidence runs up against the limits of what can be observed. Yet the multiverse hypothesis persists, not because it is proven, but because it offers a resolution to the fine-tuning problem that does not require invoking design, and it arises naturally from well-developed theories like inflation and string theory. And because it provides a framework for thinking about the ensemble of possible universes that is more concrete, more mathematically grounded than earlier speculations about parallel worlds or alternate realities. The idea that countless universes exist with different laws is not a cop-out, not a way of avoiding the question of why our universe has the laws it does, but a reframing of that question. A shift from asking why the constants are fine-tuned to asking why the multiverse as a whole has the structure it does. But whether that structure is necessary, contingent, but emergent. And if the multiverse is real, if we do live in one of the rare universes that can notice itself, then the fact that we are here to ask these questions is not a cosmic accident in the usual sense, but the inevitable outcome of a selection effect. The consequence of existing in a universe where the constants permit complexity, if chemistry can build nervous systems, if evolution can sculpt minds capable of decoding the laws that govern their own existence. The question, then, is not whether the multiverse removes meaning, but what kind of meaning it permits. If whether that meaning is diminished by the knowledge that countless other universes exist, most of them lifeless, if whether it is enriched by the realization that the universe we inhabit is one expression of a vaster reality, a single note in a cosmic symphony whose full structure we are only beginning to glimpse. The dread of randomness is real, the vertigo of existing in one bubble among an infinity of bubbles. But there is also a strange comfort in the idea that the laws of physics, but fine-tuned they appear, are not arbitrary choices made by a designer, but natural outcomes of a deeper mathematical framework, a landscape of possibilities where some regions permit life and others do not. But we find ourselves in a life-permitting region not because it was built for us, but because only such regions can produce observers. This dissolves the mystery of fine-tuning, but introduces a new mystery. Why does the multiverse exist? Why does it have the structure it does? And whether that structure itself requires explanation or whether it is simply the way things are, a brute fact of existence that admits no further justification. The multiverse as an unintended architect is a paradoxical concept, and it suggests that engineering can emerge without an engineer, that selection can produce outcomes that appear designed without requiring intention or purpose, that the fine-tuning of our universe is not evidence of a cosmic blueprint, but evidence of a vast cosmic lottery where enough tickets are drawn that even the most improbable combinations must appear. Yet this framing, while intellectually satisfying, leaves a residue of unease. While it replaces one mystery, why are the constants fine-tuned? With another, why does the multiverse exist? While why does it have the structure necessary to produce life-permitting universes? The critics are right to point out that the multiverse hypothesis is not directly testable in the way that most scientific theories are testable, that it relies on extrapolations from well-established physics into regimes where observation is impossible, and that it introduces an element of speculation that some find troubling. But the proponents are also right to argue that the multiverse is not a wild guess, but a prediction arising from theories, inflation, string theory, quantum mechanics, that have other empirical successes, and that dismissing the multiverse as metaphysics is premature when the mathematics of those theories points toward it with some insistence. What we know is this: the universe we observe is finely tuned for life, and the multiverse hypothesis offers one way to explain that fine-tuning without invoking design, by proposing that countless universes exist with different constants. And we necessarily inhabit one of the rare life-permitting universes because only they can produce observers. What we do not know is whether the multiverse is real, whether other universes actually exist, or whether they are merely mathematical constructs, artifacts of theories that work well within the observable cosmos, but whose extrapolations beyond that cosmos are speculative. The loneliness of infinite cosmic variance is not a proof against the multiverse, but a philosophical response to it, a recognition that if the multiverse is real, then our universe, our galaxy, our planet, our species, then each individual consciousness is not unique, but one instance among countless others. Then the meaning we attach to existence must be recalibrated in light of that realization, must be grounded not in cosmic uniqueness, but in something else, perhaps in the intrinsic value of experience, the irreducible fact of consciousness, the capacity for wonder and understanding that arises in rare pockets of the multiverse where the constants permit complexity. And this is where the section closes, on a question that has no easy answer. Does the multiverse remove meaning? Then does it reveal a grander cosmic ecology, a structure so vast that our universe is one cell in a living body whose full anatomy we cannot perceive? If the multiverse is real, then the fine-tuning of our universe is not a puzzle but a consequence, not evidence of design, but evidence of selection. Then the constants we measure are not arbitrary choices, but the inevitable outcome of existing in a universe where those constants permit life. If the multiverse is not real, then we are back to the original mystery, confronting the eerie precision of the constants and asking whether they point toward necessity, design. Then something else entirely, some principle or logic or structure that constrains the laws of physics in ways we have not yet understood. The multiverse hypothesis does not resolve the question of why there is something rather than nothing, but it shifts the question, broadens it, transforms it from a question about this universe to a question about the ensemble of all possible universes. But whether that ensemble is infinite, necessary, contingent, but something stranger still, something that transcends the categories of existence and non-existence and touches on the nature of reality itself, on what it means for anything to be real, but whether the answer to that question will ever be within reach of minds that arose, by chance or by necessity or by something in between, in one small corner of one universe among the countless others that may or may not exist in the vast, indifferent expanse of the multiverse. There is a threshold in the conversation about cosmic origins where speculation ceases to be merely philosophical and begins to feel testable, where the question of whether intelligence shaped the universe shifts from theology to hypothesis, where theories emerge that are strange enough to be revolutionary, yet grounded enough to be scientific. Where this threshold is where the most controversial ideas live, proposals that do not invoke gods or miracles, but instead suggests that the universe's fine-tuning might be the product of processes or entities operating according to principles we are only beginning to understand. The architect hypotheses do not require faith, but imagination, the willingness to entertain possibilities that feel absurd until you examine the mathematics and realize they are no more absurd than quantum entanglement or space-time curvature, phenomena that once seemed impossible but are now woven into the fabric of confirmed physics. These hypotheses propose that intelligence, broadly construed, not necessarily conscious, not necessarily biological, but intelligence in the sense of optimization, selection, but computation, may have played a role in shaping the constants and laws we observe, but the implications of this idea reach far beyond physics, touching on questions of purpose, agency, but the nature of existence itself. Simulation theory is perhaps the most direct form of the architect hypothesis, proposing that our universe is not a fundamental reality, but a computational construct running on hardware in a higher-level reality, a simulation created by an advanced civilization whose technology has reached the point where it can model entire universes with conscious observers who experience themselves as real. The argument, popularized by philosophers and physicists alike, runs as follows. If it is possible to create sufficiently detailed simulations of universes, and if civilizations capable of creating such simulations are not exceedingly rare, and the number of simulated universes will vastly outnumber the number of base realities, and a single advanced civilization could run countless simulations, each containing billions of years of history and trillions of conscious beings, and the statistical probability that we are living in the base reality rather than one of the simulations becomes vanishingly small. The hypothesis is not as far-fetched as it sounds, because we already create simulations of physical systems, weather models, economic projections, virtual worlds, and the trend of computational power, because it continues, suggests that within centuries or millennia our descendants might possess the ability to simulate universes at resolutions high enough that the simulated beings within them could not distinguish their reality from a fundamental one. Yet the simulation hypothesis raises profound questions about the nature of the simulator, about whether the laws of physics in our universe reflect the computational constraints of the hardware running the simulation or whether they are chosen deliberately, optimized not for biological complexity, but for computational efficiency, for the ability to run a universe that produces interesting structures without requiring prohibitive amounts of processing power. If our universe is a simulation, then the fine-tuning of the constants might not be evidence of design for life, but evidence of design for computation, for the ability to generate complexity and novelty and patterns that the simulator finds valuable or interesting or useful for purposes we cannot fathom. The cosmological constant, for instance, which determines the rate at which space expands, might be tuned not to permit galaxies and stars, but to ensure that the simulation runs at a pace that balances computational cost against the richness of the phenomena it produces. The speed of light, which sets the maximum rate at which information can propagate through space, might be a computational bottleneck, a limit imposed by the processing speed of the hardware, and the quantization of energy and spacetime at the Planck scale might reflect the discrete nature of the simulation's underlying grid, the voxels or pixels from which reality is constructed. But there is a deeper problem with the simulation hypothesis, and it merely relocates the question of origins rather than answering it. If our universe is a simulation, and what is the nature of the reality that contains the simulator? And where did that reality come from? And are its laws fine-tuned as well, requiring their own explanation, leading to an infinite regress of simulations nested within simulations? The hypothesis does not resolve the mystery of existence, but shifts it to a higher level. And while it offers a framework for thinking about the universe as computation, it leaves unanswered the question of why computation should be possible at all, why there should be any reality, base or simulated, capable of supporting the kind of information processing necessary to run a universe. Yet the simulation hypothesis is testable, at least in principle. Because simulations have limits, because those limits might leave detectable signatures, glitches in the laws of physics, inconsistencies at extreme scales, patterns in the cosmic microwave background, or the distribution of galaxies that reveal the underlying grid structure, because violations of continuous symmetry that betray the discrete nature of the simulation's computational substrate. Physicists have searched for such anomalies without finding convincing evidence. But the absence of evidence is not evidence of absence. But the possibility remains that our universe is a simulation whose resolution and computational power are high enough that we cannot yet detect the seams. Cosmic natural selection, proposed by the physicist Lee Smolin, offers a different form of the architect hypothesis, one that does not require a conscious designer, but instead suggests that universes evolve through a process analogous to biological natural selection. But black holes serve as the mechanism of reproduction, each black hole spawning a new universe with slightly different constants. But those universes that produce more black holes leave more offspring, leading to a population of universes dominated by those whose parameters are optimized for black hole production. The hypothesis is elegant because it provides a naturalistic explanation for fine-tuning without invoking design or coincidence, suggesting instead that the constants we observe are the result of an evolutionary process operating across countless generations of universes. And our universe, with its particular values for the gravitational constant, the masses of particles, and the cosmological constant, is a descendant of universes that came before, shaped by selection pressures that favored the production of black holes. The mechanism is surprisingly concrete. When matter collapses to form a black hole, general relativity predicts that space-time curvature becomes infinite at the singularity. But Smolin proposes that instead of a true singularity, what occurs is a bounce, a quantum process that transforms the collapsing matter into the seed of a new universe, a Big Bang on the other side of the event horizon. But this new universe inherits the constants of its parent universe with small random variations, analogous to mutations in biological reproduction. Yet the truth may be stranger, but if cosmic natural selection is real. But the fine-tuning of our universe is not optimized for life, but for black holes. But life, consciousness, but complexity are incidental byproducts, side effects of a universe whose constants happen to permit both black hole production and the emergence of observers capable of asking why the universe has the structure it does. Smolin's hypothesis makes testable predictions. If the constants are optimized for black hole production, then small changes to those constants should decrease the number of black holes. Then calculations suggest that this is indeed the case for many of the fundamental parameters, lending some support to the idea. The strong nuclear force, for instance, is tuned such that neutron stars can collapse into black holes under certain conditions. And if the force were slightly different, either too few or too many black holes would form, reducing the reproductive success of the universe. The cosmological constant, which determines the rate of expansion, is small enough that galaxies can form and stars can collapse into black holes before space expands so rapidly that structure formation ceases. And this balance between expansion and collapse is critical for maximizing black hole production. The hypothesis is not without its critics, who point out that the mechanism by which black holes spawn new universes is speculative, not confirmed by quantum gravity theories, and that the idea of universes reproducing through black holes is more metaphor than mechanism, a suggestive analogy rather than a fully developed physical theory. And this is where the story bends toward the uncanny. And if cosmic natural selection is real, and the universe has a kind of purpose, not in the teleological sense of a goal imposed from outside, but in the evolutionary sense of a function that emerges from the reproductive dynamics of the system, and that function is to produce black holes, to maximize the number of offspring universes. And everything else, stars, planets, chemistry, life, consciousness, is incidental, a side effect of the parameters necessary to make black holes efficiently. Yet there is a deeper implication, suggested by some theorists who have extended Smolin's idea. If intelligence arises in a universe, and if that intelligence becomes advanced enough to manipulate the constants of physics or to engineer black holes deliberately, and intelligence itself could become a mechanism of cosmic reproduction, guiding the formation of black holes and influencing the constants of offspring universes in ways that natural processes alone could not achieve. This variant, called cosmological natural selection with intelligence, proposes that advanced civilizations, once they reach a certain level of technological capability, might engineer black holes not as byproducts of stellar collapse, but as deliberate acts of universe creation, fine-tuning the conditions inside those black holes to produce offspring universes with desirable properties. And if this process occurs, and intelligence becomes part of the evolutionary dynamics of the multiverse, and the fine-tuning we observe might reflect not merely the optimization for black holes, but the optimization for the emergence of intelligence capable of creating more universes. But there is a deeper problem lurking in this framework, and if intelligence can engineer universes. And the question of whether our universe was engineered becomes unavoidable, and the fine-tuning of the constants might not be the result of blind evolutionary processes, but the deliberate choice of a predecessor civilization, an ancient intelligence that existed in a parent universe and used a black hole as the mechanism to birth our universe, calibrating the constants to produce a cosmos capable of supporting life, complexity, and eventually intelligence that could continue the process. This idea, while speculative, is not metaphysical but scientific in principle. While it makes predictions, if our universe was engineered by a predecessor civilization, while the constants should be optimized not just for black holes but for the emergence of intelligence, while there might be signatures in the laws of physics, regularities, patterns, while structures that reveal the hand of the engineer, much as the code of a software program reveals the intentions of the programmer. The search for such signatures is ongoing, and while no convincing evidence has been found, the possibility remains that the universe contains messages or markers encoded in the cosmic microwave background or the distribution of galaxies or the mathematical structure of the laws themselves, waiting to be decoded by civilizations advanced enough to recognize them. Yet the question persists: if intelligence shaped our universe, and is it now? And would we ever recognize it? If the engineer was a civilization in a parent universe, then it exists on the other side of the black hole from which our universe emerged, separated from us by an event horizon that prevents any causal contact, any communication, any possibility of interaction. Then the only evidence of its existence would be the fine-tuning of the constants themselves, the eerie precision that suggests intentionality but offers no direct proof. Or perhaps the intelligence is not external but internal, not a predecessor civilization but an emergent property of the universe itself, a form of cosmic intelligence that arises not from brains or computers but from the collective dynamics of matter and energy and space-time, a distributed computation that processes information at scales far beyond what biological minds can comprehend. And the laws of physics are not imposed from outside but emerge from the self-organizing behavior of this cosmic intelligence, executing algorithms whose purpose and logic remain opaque to us. This idea, while even more speculative, is grounded in observations of how complex systems self-organize, how patterns and structures emerge from simple rules, while how information processing occurs not just in brains and computers, but in any system where inputs are transformed into outputs according to consistent principles. The possibility of universe-creating civilizations, advanced beings who have mastered the physics of black holes and learned to engineer the conditions inside them to produce offspring universes with specific properties, is not science fiction, but a logical extension of what we already know about technology and physics. If civilizations can arise, and if they can survive long enough to develop technologies capable of manipulating space-time and matter at the scales necessary to create black holes, and it is plausible that such civilizations would experiment with universe creation, either as a form of ultimate engineering or as a means of ensuring their legacy, encoding their knowledge and values into the structure of offspring universes that would outlive them. The fine-tuning we observe might be the signature of such a project. The universe we inhabit not a natural outcome, but a designed artifact, created by beings who existed in a parent universe, and who chose the constants carefully to maximize the chances that intelligence would arise and continue the process. This hypothesis is both awe-inspiring and unsettling, because it suggests that we are not the first intelligent beings in the cosmic lineage, that our existence is the result of a deliberate act by entities whose nature and motivations we can only guess at. Because that the purpose of our universe, because it has one, might be to produce civilizations capable of creating new universes in turn, a kind of cosmic reproduction where intelligence is the mechanism and the universe is the offspring. Yet the fear of being unable to detect such engineers, because they exist, is profound. Because the timescales and distances involved are so vast that any signals or artifacts they left behind might be unrecognizable to us, might be encoded in structures or phenomena that we observe but do not understand. Because the markers of their intelligence might be so subtle, so deeply woven into the fabric of the laws of physics, that we could be looking directly at them without realizing what they are. The cosmic microwave background, that faint glow of radiation from the early universe, might contain patterns that are not random but deliberate, messages encoded in the temperature fluctuations or the polarization of the light, waiting to be decoded by civilizations advanced enough to recognize them as signals rather than noise. The structure of space-time itself, the way that gravity and quantum mechanics intertwine, might be optimized not just for physics but for computation, for the ability to process information in ways that biological minds cannot. And the universe might be running a computation whose purpose and output remain beyond our comprehension. A calculation so vast and complex that conscious beings like us are merely intermediate steps, subroutines in a program whose full logic we cannot access. And this is where the story reaches its emotional cliffhanger, and the architect hypotheses, whether framed as simulation theory, cosmic natural selection, and universe-creating civilizations, all converge on the same unsettling realization. If intelligence shaped our universe, and we are not the beginning but a continuation, not the first but the inheritors of a cosmic lineage that stretches back through generations of universes, each one giving rise to the next. And the fine-tuning we observe is not evidence of a singular creation event, but evidence of a process, an evolutionary or engineering process that has been unfolding across timescales and scales so vast that the entire history of our universe, from the Big Bang to the present, is a single tick in a clock that has been running for far longer than we can imagine. If cosmic natural selection is real, then our universe is a descendant of universes that came before, shaped by selection pressures that favored the production of black holes and, incidentally, the emergence of complexity and consciousness. If simulation theory is correct, then our universe is a computational artifact created by beings in a higher-level reality whose motivations and nature are as opaque to us as our motivations would be to the characters in a video game. If universe-creating civilizations exist, then the constants of our universe might be the deliberate choices of engineers who preceded us, who existed in a parent universe and used a black hole as the mechanism to birth our cosmos, fine-tuning the parameters to maximize the chances that intelligence would arise and continue the cosmic reproductive cycle. The question, then, is not whether these hypotheses are true, but whether they are testable, whether they make predictions that can be confirmed or falsified by observation. Then whether the evidence we gather from telescopes and particle accelerators and gravitational wave detectors can distinguish between a universe that arose by chance, a universe that emerged from evolutionary processes, then a universe that was engineered by intelligence. Cosmic natural selection makes specific predictions about the distribution of constants and the number of black holes, predictions that can be tested by comparing the observed properties of our universe with the properties of hypothetical universes where the constants are slightly different. Simulation theory predicts that there might be computational limits or artifacts in the laws of physics, signatures of the underlying grid or processing constraints that reveal the simulated nature of reality. Universe-creating civilizations might leave markers or messages encoded in the structure of the cosmos, patterns that are too regular, too precise, too mathematically elegant to be the result of natural processes alone. The search for such evidence is ongoing. And while no definitive proof has been found, the absence of evidence is not evidence of absence. And the possibility remains that the universe contains clues to its origins that we have not yet learned to recognize, that the fine-tuning we observe is not merely a puzzle but a message, a signal from the architects, and they exist, announcing their presence in the only language that transcends universes, the language of mathematics and physical law. Yet the emotional weight of the architect hypotheses is not in the mathematics, but in the implications, in what it would mean for our place in the cosmos if intelligence did shape the universe. And we are not accidents, but products of a process that extends far beyond our own existence. And the purpose of the universe is not to produce stars and galaxies, but to produce beings capable of understanding, capable of creating, capable of continuing the cosmic lineage by engineering universes of their own. This is both humbling and elevating, because it suggests that consciousness is not an accident, not a byproduct of chemistry and evolution, because a feature, a function, perhaps even the function of the universe, the mechanism by which the cosmos reproduces, understands itself, because propagates forward through time and space into configurations and possibilities that we can barely imagine. If the architects exist, they are not gods but engineers, not omnipotent but advanced, not eternal but mortal, beings who arose in universes that came before ours and who used the tools available to them. Black holes, quantum fields, the plasticity of physical constants, to create offspring universes, to encode their knowledge and their hopes into the structure of reality itself, and to set in motion processes that would, given enough time, lead to the emergence of civilizations like ours, capable of asking the same questions they once asked, capable of reaching the same conclusions they once reached, capable of creating new universes and continuing the cycle. And so the section closes on the most profound question of all. If intelligence shaped our universe, and is it now? Is it on the other side of the black hole from which our cosmos emerged, separated from us by an event horizon that prevents any contact, any communication, any possibility of ever knowing who they were or what they intended? Is it embedded in the laws of physics themselves, not as a conscious entity, but as an informational residue? The mathematical structure of the universe encoding the principles and purposes of the engineers who designed it? Or is it yet to come, not behind us, but ahead of us, not an apparent universe, but in the future of our own, waiting for civilizations like ours to reach the level of capability necessary to engineer black holes, to manipulate constants, to create offspring universes, and to become, in our turn, the architects of realities we cannot yet imagine? And the deeper question, the one that lingers after all the theories and hypotheses and calculations have been considered, would we ever recognize the architects if we encountered evidence of them? Or are their signatures so deeply woven into the fabric of reality, so abstract and mathematical and alien to our ways of thinking, that we could be living inside their creation, obeying their laws, fulfilling their purposes, without ever realizing that the universe is not just a place we inhabit, but a message we are meant to decode, a signal from intelligences that preceded us, announcing their existence in the only way that survives the passage of universes, through the fine-tuning of the constants, through the elegance of the equations, through the improbable precision that allows complexity, consciousness, or the capacity to ask why. There is another way to look at the universe's eerie precision, another lens through which the appearance of design dissolves not into randomness or multiverse or architect, but into something more fundamental. The generative power of simple rules operating on themselves, the capacity of chaos to spontaneously organize into structure, the emergence of complexity from simplicity without guidance, without intention, without any need for a blueprint, because the blueprint is written into the rules themselves and those rules, and allowed to iterate across scales and time, produce galaxies, snowflakes, neural networks, and consciousness as naturally as a river carves a canyon or a crystal grows from a seed. Emergence is the phenomenon where systems exhibit behaviors and properties that their individual components do not possess, where the whole becomes greater than the sum of its parts not through addition but through interaction, through the way that simple entities following simple rules give rise to patterns so intricate, so organized, so seemingly purposeful that they feel designed even though no designer exists, no intelligence orchestrates the outcome, no hand guides the process from chaos to order. Consider a snowflake, that icon of natural geometry, whose sixfold symmetry and fractal branching arise not from a template or a plan, but from the physics of water molecules as they transition from vapor to ice, each molecule binding to others according to the angles dictated by hydrogen bonds. where those angles, repeated across millions of molecules, generate the macroscopic structure we observe, unique in detail but universal in form, where no two snowflakes are identical yet all are. Recognizably snowflakes, variations on a theme encoded not in genes or blueprints, but in the electromagnetic forces that govern how atoms interact. Or consider a flock of birds, thousands of individuals moving as one, turning and diving in synchronized waves that flow across the sky like liquid. And yet there is no leader, no commander directing the motion, only local rules: stay close to your neighbors, match their velocity, avoid collisions. And these simple rules, applied by each bird to the birds around it, generate the emergent behavior of the flock, a collective pattern that no individual bird comprehends but that arises inevitably from the interactions. An ant colony operates on similar principles, with no centralized decision-making, no queen issuing commands, yet the colony exhibits problem-solving behavior, building complex nests, foraging efficiently, defending against threats, and adapting to changing conditions, all because individual ants respond to chemical signals, pheromones, and those responses, aggregated across thousands or millions of ants, produce outcomes that look intelligent, purposeful, coordinated, even though each ant is following rules far simpler than the behavior of the colony as a whole. Yet the truth is that emergence is not limited to biology or visible scales, but pervades the universe at every level, from the quantum to the cosmic, from the interactions of subatomic particles to the formation of galaxies. In physics, magnetism emerges from the alignment of electron spins in a material, and no single electron is magnetic. And when billions of them spontaneously align their magnetic moments at temperatures below a critical threshold, the material as a whole becomes magnetic, exhibiting a property that does not exist at the level of individual electrons but emerges from their collective behavior. Superconductivity, where electrical resistance vanishes at temperatures near absolute zero, emerges from the cooperative flow of electrons forming Cooper pairs, quantum mechanically entangled in ways that allow them to move through a lattice without scattering. Where this emergent phenomenon cannot be predicted from the behavior of individual electrons, but arises only when you consider the interactions of countless electrons with each other and with the atomic lattice. On cosmological scales, the structure of the universe, the filaments and voids, the clusters and superclusters of galaxies, emerges from the gravitational attraction of matter, amplifying the tiny density fluctuations imprinted during inflation, and the cosmic web we observe today, stretching across billions of light years, is an emergent pattern arising from the interplay of gravity, dark matter, and the expansion of space. And this is where the lens shifts. And if complexity arises spontaneously from simplicity, and order flowers out of chaos without need for guidance, and the fine-tuning of the universe may not be evidence of design, but evidence of emergence, the natural outcome of rules that permit self-organization, that allow systems to explore the space of possible configurations and settle into patterns that maximize some quantity, entropy, stability, connectivity, or that minimize energy. And the universe we observe, with its stars and galaxies and life, is one such pattern, an attractor in the space of possible universes, not unique but probable, not designed but inevitable given the rules that govern how matter and energy interact. The constants themselves, the fine-tuned parameters that seem so improbable, might be emergent properties rather than fundamental inputs, values that arise not because they were chosen, but because they are the only values consistent with a self-organizing universe, the only configurations that allow structure to persist and complexity to grow without collapsing into uniformity or exploding into chaos. But there is a deeper problem lurking in this framework. Because even if complexity emerges without guidance, even if order arises spontaneously from chaos, we are still left with the question of why the rules that allow emergence exist in the first place. Why does the universe follow rules at all, and why are those rules mathematical, elegant, consistent across space and time? And why do they permit the kind of interactions, gravity, electromagnetism, quantum mechanics, that lead to self-organization rather than dissolution, to structure rather than featurelessness? The emergentist answer dissolves the mystery of how complexity arises, but does not dissolve the mystery of why the substrate from which complexity emerges has the properties it does, why space-time is four-dimensional, why particles obey quantum statistics, why forces fall off with distance according to inverse square laws, and whether these properties are themselves emergent, arising from even deeper principles, and whether they are fundamental, brute facts of existence that admit no further explanation. Yet the paradox of spontaneous order is that it feels uncanny, unnatural, counterintuitive, and our everyday experience teaches us that systems tend toward disorder, that entropy increases, that structure decays, and the second law of thermodynamics, which states that the entropy of a closed system never decreases, seems to contradict the emergence of complexity, the appearance of order from chaos, the formation of galaxies and stars and planets and life in a universe that is, on the whole, running down, cooling off, expanding toward a state of maximum entropy where no gradients remain, no structure persists, no complexity survives. But the resolution is subtle. The second law applies to closed systems, and the universe as a whole may be closed, and subsystems within the universe are open, exchanging energy and matter with their surroundings. And in such open systems, local decreases in entropy, local increases in order, can occur as long as they are paid for by larger increases in entropy elsewhere. And this is how complexity arises. Stars form by gravitational collapse, concentrating matter and lowering entropy locally, and in the process they radiate energy into space, increasing the entropy of the environment by a greater amount. And the net result is an overall increase in entropy even as local pockets of order emerge. And this is where the story bends toward the generative power of chaos, and chaos in the technical sense. Systems that are sensitive to initial conditions and small differences in starting states lead to wildly divergent outcomes, is not the opposite of order but the engine of complexity, the mechanism by which simple deterministic rules can produce unpredictable, rich, varied behavior. The Mandelbrot set, that fractal icon of mathematical beauty, emerges from the repeated application of a simple equation to complex numbers, and the boundary of the set, infinitely detailed, never repeating, exhibits structure at every scale, patterns within patterns within patterns, and no amount of computation can exhaust the richness encoded in that simple iterative rule. Cellular automata, simple computational models where cells in a grid evolve according to rules based on the states of their neighbors, can produce astonishingly complex behaviors from trivially simple starting conditions. Conway's Game of Life, for instance, uses just 4 rules: birth, survival, loneliness, overcrowding, and from these rules emerge gliders, oscillators, self-replicating structures, and patterns that seem alive, that exhibit growth and decay and interaction, all without any underlying program or design beyond the rules themselves. Yet the uncanny similarity between natural and engineered systems is unsettling, and the patterns that emerge from simple rules, fractals, networks, power laws, scale invariance, are the same patterns we observe in nature, in the branching of trees and rivers, in the distribution of galaxy clusters, in the connectivity of neural networks and the internet, in the frequency of earthquakes and the sizes of cities. And this universality suggests that there are deep principles governing how complexity arises, principles that transcend the specific details of the system, whether it is biological, physical, social, and computational. Network theory reveals that many natural systems, food webs, metabolic pathways, the structure of the brain, the World Wide Web, are scale-free networks, where the distribution of connections follows a power law, with a few nodes having many connections and most nodes having few, where these networks are robust to random failures but vulnerable to targeted attacks, where they arise naturally from processes of preferential attachment, where new nodes are more likely to connect to nodes that already have many connections, a rich-get-richer dynamic that requires no central planner but emerges from local decisions. The structure of galaxies themselves, the spiral arms and bars and halos, emerge from gravitational interactions and the differential rotation of matter, where computer simulations show that you can start with a nearly uniform distribution of matter, apply gravity, and let the system evolve, where out come structures that look remarkably like the galaxies we observe, not because the simulation was programmed to produce galaxies, but because gravitational collapse and angular momentum conservation naturally generates spiral patterns, density waves, where hierarchical clustering, life itself, that most complex of phenomena, is an emergent property of chemistry, arising when molecules capable of self-replication, metabolism, and evolution come together in configurations that can harness energy gradients, maintain themselves against the second law of thermodynamics by increasing entropy in their surroundings, and adapt to changing conditions through variation and selection. No single molecule is alive. One amino acid is not alive. One nucleotide is not alive. But when they interact in the right ways, when they form polymers and membranes and metabolic networks, when they couple replication to mutation and link survival to function, when something new emerges, something that exhibits the properties we call life, even though those properties do not exist at the level of the individual molecules. And this is where the question sharpens. Can complexity arise without a designer? When does the capacity for self-organization itself require explanation? When if the universe is structured such that chaos bends into patterns, that disorder spontaneously organizes into order, when is that structure designed, tuned, fine-tuned to permit emergence? When is it inevitable, the only way a universe could be? The physicist Philip Anderson, in a famous essay titled "More is Different," argued that at each level of complexity, new laws emerge that cannot be reduced to the laws of the level below, that the properties of materials, of life, of consciousness, are not merely consequences of particle physics, but are genuinely novel phenomena requiring their own principles and frameworks. This is a form of weak emergence, where the macro-level behavior, where in principle derivable from the micro-level rules, is not predictable in practice because the computation required to trace all the interactions is prohibitively complex, where new concepts, temperature, pressure, life, consciousness, are necessary to describe and understand the system. But there is also the possibility of strong emergence, where the macro-level properties are not derivable even in principle from the micro-level rules, where genuinely novel laws appear that have no counterpart at lower levels, where some physicists argue that phenomena like superconductivity or the arrow of time, or even consciousness itself may be examples of strong emergence, properties that transcend the sum of their parts in a fundamental way. Yet even if we grant that complexity emerges without guidance, that order arises spontaneously from chaos, we are confronted with the unsettling question of why the rules that allow emergence exist in the first place, why the universe is governed by laws that permit self-organization, that encourage structure formation, that allow local pockets of complexity to arise and persist despite the overall trend toward entropy and heat death. The emergentist framework explains how, but not why, but the why question remains as mysterious as ever, pointing toward deeper principles or necessities, or perhaps toward the recognition that the why question itself may be unanswerable, that the rules are simply the way things are, brute facts of existence that require no justification, because there is no alternative, no other way for a universe to be. Perhaps the universe looks engineered because chaos itself is generative, because the dynamics of matter and energy naturally explore the space of possible configurations and settle into patterns that exhibit order, symmetry, complexity, because the appearance of purpose. Because what we interpret as design is merely the inevitable outcome of rules that permit exploration, variation, because selection at scales from atoms to galaxies. But the deeper disquiet remains. If order and complexity are inevitable, because the universe is structured such that emergence is not the exception but the rule. Because what does that say about the nature of existence? Does it mean that the fine-tuning we observe is not fine-tuning at all, but the natural consequence of rules that inevitably lead to structure and complexity? That any universe with laws permitting interaction and iteration will eventually produce stars, chemistry, and perhaps life? And our universe is not special but typical, one instance of a universal tendency toward increasing complexity even as entropy increases? Or does it mean that the rules themselves are fine-tuned, that the capacity for emergence requires specific properties, dimensionality, force laws, conservation principles, that are themselves improbable, and the emergence framework merely shifts the question from why the constants are tuned to why the rules permit emergence? The answer is not clear, and physicists and philosophers remain divided. Some arguing that emergence dissolves the fine-tuning problem by showing that complexity arises naturally. Others arguing that emergence deepens the problem by revealing that the rules themselves require explanation. And so the section closes on a soft cliffhanger toward the philosophical. If order and complexity are inevitable, and chaos bends into patterns not because it is guided, but because the rules allow it, encourage it, make it the natural outcome of iterating simple interactions across time and space. And the universe we observe, with its galaxies and stars and planets and life and consciousness, is not an accident, not a rare fluctuation, not a designed artifact, and an expected result, a natural expression of the generative power of the laws of physics. Yet this inevitability is not comforting but uncanny, because it suggests that the universe could not have been otherwise, that the appearance of structure and complexity is not contingent but necessary, woven into the fabric of reality itself, because the question of why the fabric has the properties it does, why spacetime, why quantum fields, why forces that decrease with distance, why conservation laws, remains unanswered, perhaps unanswerable, a mystery that emergence explains at one level but deepens at another. The paradox of spontaneous order is that it feels too easy, too elegant, too much like magic, that something as intricate as a snowflake or a galaxy or a brain can arise from nothing more than simple rules and local interactions. And yet this is what the evidence shows, what the simulations demonstrate, what the mathematics predicts, and the uncanny similarity between natural and engineered systems is not evidence that natural systems are engineered, but evidence that engineering, and it works, mimics the principles of emergence, harnesses the generative power of simple rules to produce complex outcomes. And the universe, in this view, is the ultimate self-organizing system, a cosmos that engineers itself into existence not through intention, but through the inevitable unfolding of rules that permit structure, complexity, and the capacity to ask why. There is a quieter possibility, one that shifts the question away from the universe and toward the observer, toward the minds that contemplate cosmic structure and see in it patterns, purposes, symmetries that may say more about the architecture of consciousness than the architecture of the cosmos. Human brains did not evolve to understand quantum fields or cosmological constants, but to survive in environments where detecting patterns meant the difference between eating and being eaten, where assigning agency to rustling grass, assuming a predator even when none was there, carried less cost than failing to detect a real threat, where this cognitive bias, this hyperactive pattern detection, this tendency to see faces in clouds and intention in randomness, is woven into the neural circuits that generate our experience of reality. We are pattern-seeking creatures, shaped by natural selection to impose order on chaos, to construct narratives that link cause and effect, to perceive design even in systems governed by nothing more than probability and iteration. And the question arises whether the fine-tuning we observe, the eerie precision of cosmic constants, the appearance of engineering in the laws of physics, is a property of the universe or a projection of minds evolved to detect agency, purpose, and structure where none exists. The phenomenon is not limited to cosmic speculation, but pervades human cognition at every level, from the pareidolia that makes us see faces in the moon and in burnt toast to the apophenia that finds meaningful connections in unrelated events, from the gambler's fallacy that detects patterns in random sequences to the conspiracy theories that weave elaborate narratives from coincidences. The brain is a prediction machine, constantly generating models of the world based on past experience and sensory input, and those models are not passive representations, but active constructions, shaped by expectations and biases and the cognitive tools available to the organism doing the modeling. When we look at the universe and see design, we may be observing a genuine feature of reality, or we may be observing the way our brains process information, the way that neural networks trained on survival in African savannas respond when confronted with the mathematical structure of quantum field theory and the statistical improbability of life-permitting constants. The appearance of intention, the feeling that the universe is built for something, may be an artifact of consciousness, a side effect of having minds capable of asking why. And the question of whether the universe is fine-tuned becomes entangled with the question of whether consciousness itself, with its biases and heuristics and narrative-building capacities, is capable of perceiving reality as it is, or whether perception is always and inevitably a construction, an interpretation, a story we tell ourselves about patterns that may or may not correspond to structures independent of the storyteller. Yet quantum mechanics complicates this picture profoundly. An observation in quantum theory is not passive but active, not a mere recording of pre-existing facts, but an intervention that affects the system being observed, that forces potentialities into actualities, that collapses wave functions and determines outcomes in ways that classical physics never required. The double-slit experiment, where particles behave as waves when unobserved and as particles when measured, suggests that the act of observation, the presence of a detector or a conscious observer, plays a role in determining physical outcomes. Where this has led some physicists and philosophers to propose that consciousness is not a byproduct of physical processes, but a fundamental ingredient of reality, that the universe requires observers to actualize its potential states, that without consciousness there would be only superpositions, only unresolved probabilities, only a reality that exists in some abstract mathematical sense, but never manifests as definite, concrete, experienced phenomena. This interpretation, while controversial, is not fringe speculation but arises from taking the mathematics of quantum mechanics seriously, from asking what it means for a system to exist in a superposition of states until measured. While whether measurement requires consciousness or whether any physical interaction suffices to collapse the wave function. The physicist John Wheeler, contemplating the implications of quantum mechanics for cosmology, proposed a concept he called the participatory universe, suggesting that observers are not external to reality but integral to it, that the act of observation brings the universe into being in a retrospective sense, determining not just present outcomes, but the entire history leading up to those outcomes. Wheeler's thought experiments, including the delayed choice experiment where decisions about measurement can be made after a photon has already passed through a double slit, demonstrate that the distinction between past and present, between what has happened and what is observed to have happened, becomes blurred in quantum mechanics, and if observers play a role in determining the past. And consciousness is not merely witnessing reality, but participates in its construction. This idea is both exhilarating and vertiginous, because it suggests that the universe we observe is not independent of the observers doing the observing, that the fine-tuning of constants, the structure of galaxies, the history of cosmic evolution, are all entangled with the fact that conscious beings exist to observe them. Because the appearance of design may reflect not a blueprint imposed from outside, but the interaction between mind and matter, between the quantum substrate of reality and the conscious processes that actualize specific configurations from among the infinite possibilities encoded in the wave function of the universe. And this is where theories of consciousness as a fundamental feature of reality begin to take shape, not as mysticism, but as serious proposals attempting to reconcile the subjective character of experience with the objective structure of physics. Panpsychism, the ancient idea that consciousness is a fundamental property of matter, has been revived by contemporary philosophers who argue that the hard problem of consciousness, the question of how subjective experience arises from objective physical processes, may be insoluble if we assume that consciousness emerges only at high levels of neural complexity, but becomes tractable if we posit that even simple systems possess some primitive form of experience, some proto-consciousness that combines and intensifies as systems become more complex. In this view, electrons and quarks are not conscious in the way humans are conscious, but they possess some minimal experiential quality, some intrinsic aspect that aggregates into the rich inner lives of organisms with brains and nervous systems. But consciousness is not something that appears suddenly when matter is organized in certain ways, but is present all along, woven into the fabric of reality at the most fundamental level. Integrated information theory, developed by the neuroscientist Giulio Tononi, offers a more formal approach, proposing that consciousness is identical to integrated information, quantified by a measure called phi, which captures the degree to which a system is both differentiated and unified, capable of generating many distinct states while maintaining coherent integration across those states. A system with high phi, like the human brain, with billions of neurons interconnected in complex patterns, possesses high levels of consciousness, while systems with low phi, like a collection of isolated processors or a grid of non-interacting elements, possess little or no consciousness. The theory makes testable predictions about which systems should be conscious and which should not, and it suggests that consciousness is not limited to biological brains, but could arise in any system with the right kind of information integration, including, potentially, sufficiently advanced artificial intelligences, or even, speculatively, the universe itself if its structure permits the kind of integrated information processing that the theory identifies with consciousness. Yet the truth may be stranger. In quantum cognition, the application of quantum mechanical formalism to model cognitive processes suggests that the brain might exploit quantum effects, superposition, entanglement, interference, to perform computations that classical neural networks cannot, and if consciousness involves quantum processes. And the boundary between observer and observed, between mind and matter, becomes even more blurred, and quantum systems are inherently non-local, entangled across space and time in ways that defy classical intuitions about separability and independence. Roger Penrose and Stuart Hameroff have proposed that microtubules, structural proteins inside neurons, might support quantum coherence at temperatures and timescales relevant to brain function, and that consciousness arises from the orchestrated collapse of quantum superpositions within these microtubules, a process they call orchestrated objective reduction. The hypothesis is controversial, and many neuroscientists argue that the brain is too warm and wet to support quantum coherence, that decoherence would destroy any quantum states too quickly for them to play a functional role. And the debate remains open, and experiments are ongoing to determine whether quantum effects occur in biological systems and whether they contribute to the phenomena we associate with consciousness. But there is a deeper problem lurking in the intersection of consciousness and cosmology. And if observation plays a role in actualizing reality, and consciousness is required to collapse wave functions and determine outcomes, and the early universe and any observers existed becomes a paradox, a quantum system in superposition with no one to observe it, no mechanism to collapse the wave function and produce the definite history of cosmic evolution that we infer from the cosmic microwave background and the distribution of galaxies. The anthropic resolution to this paradox suggests that observers are not required at every moment, but only eventually, that the universe exists in superposition until conscious beings arise, and at that point the wave function collapses retrospectively, determining the entire history in a way consistent with the observations being made. And this backward causation, and bizarre, is permitted by the mathematics of quantum mechanics and has been demonstrated in delayed choice experiments. In this view, the universe we observe is selected from among all possible histories by the constraint that it must be capable of producing observers, and the fine-tuning of constants is not evidence of design, but evidence that we are sampling from the subset of quantum histories where observers exist to sample. And this is where the question sharpens. Do we see design because it is there? And because we must? If consciousness is a pattern-detecting, narrative-building process shaped by evolution to impose order on chaos, to perceive agency and purpose and structure even where none exists, then the appearance of design in the universe may be an illusion, a cognitive artifact, a projection of minds onto a reality that is indifferent to meaning, pattern, than purpose. But if consciousness is fundamental, if observers play a role in actualizing reality, if the universe requires minds to collapse its quantum potentials into definite states, if the appearance of design may reflect something deeper, a genuine entanglement between mind and cosmos, a participatory relationship where the structure of reality and the structure of consciousness are not separate but codependent, mutually shaping each other in ways that blur the distinction between subject and object, between observer and observed. The existential weight of observation is profound. If consciousness shapes reality, if we are not passive witnesses to the universe, but active participants in its unfolding, not discovering pre-existing truths, but constructing them through the act of measurement, through the questions we ask and the experiments we perform and the patterns we perceive. This is both empowering and terrifying, because it suggests that the universe we know is inseparable from the knowing, that the cosmos we describe is entangled with the consciousness doing the describing. Because that the search for objective truth, for reality as it is independent of observers, may be misguided because there is no such independence, no view from nowhere, no way to step outside the participatory relationship and see the universe as it would be if no one were looking. The fine-tuning we observe, the eerie precision of the constants, the appearance of a universe structured to produce observers, may be tautological. Of course, the universe we observe is capable of producing observers. Because we are the observers, because any universe we could observe must be one where observation is possible. But this tautology does not dissolve the mystery so much as relocate it, shifting the question from why the universe is fine-tuned to why consciousness exists, why matter is capable of organizing itself into structures that experience, that reflect, that wonder. Because whether consciousness is a rare accident or an inevitable outcome, a fundamental feature of reality, or an emergent phenomenon that appears only under specific conditions, the blurring of mind and matter is not metaphor, but may be literal, encoded in the mathematics of quantum mechanics, in the way that measurement collapses superpositions, in the way that entanglement links systems across space, in the way that information, the fundamental currency of both physics and consciousness, flows through reality, transforming potentials into actualities, uncertainties into definite outcomes. If the universe is fundamentally informational, if particles are not things but processes, if space-time is emergent from deeper quantum relationships, if consciousness, which is also fundamentally about processing information, about integrating inputs into unified experiences, about generating representations of reality and acting on those representations, may be less anomalous than it seems. Not a strange epiphenomenon arising from complicated arrangements of atoms, but a natural feature of systems capable of processing information in integrated, differentiated ways. The cosmos may be aware of itself through us, not in the sense that the universe as a whole possesses a unified consciousness akin to a mind, but in the sense that consciousness is the mechanism by which the universe's potential becomes actual, by which quantum possibilities resolve into experienced realities, by which information encoded in fields and forces manifests as the rich phenomenology of lived experience. And so the section closes on a question that has no easy answer, that touches the boundary between physics and philosophy, between neuroscience and metaphysics. Do we see design because it is there, but because we must? If consciousness is a projection, a pattern imposed by evolved neural circuits onto a reality that contains no patterns, then the fine-tuning problem is a cognitive illusion, a failure to recognize that our perception of order, symmetry. Then purpose is not a feature of the cosmos, but a feature of the brains that evolved to navigate complex environments by detecting patterns even where none exist. But if consciousness is fundamental, if observation actualizes reality, if the universe requires minds to collapse its quantum states into definite histories, if the appearance of design may be real, not in the sense of a blueprint imposed by an external architect, but in the sense of a participatory process where mind and matter, observer and observed, consciousness and cosmos, are not separate entities but aspects of a single unified reality whose structure emerges from the interaction between what is possible and what is observed. The existential weight of this realization is that we cannot step outside our consciousness to see the universe as it would be without observers, cannot disentangle the structure of reality from the structure of the minds perceiving it. And the question of whether the universe is engineered becomes inseparable from the question of what consciousness is and it comes from, and whether the capacity to ask why is itself evidence of something deeper, a cosmic tendency towards self-awareness, a universe that evolves not just stars and galaxies, but minds capable of understanding their own existence, and in that understanding, perhaps, participating in the very process that brought them into being. There comes a moment, after wandering through hypotheses of multiverses and architects and emergent order and conscious observers. After the question narrows to a single point, sharp and unavoidable. Does the universe have purpose? Not the purpose assigned by human minds, not the goals we project onto nature, but something intrinsic, something woven into the fabric of reality itself, a directionality or tendency or teleology that makes the cosmos more than a mechanical system executing equations, but a process unfolding towards something, seeking something, becoming something that it was not at the beginning. Purpose is a dangerous word in science, tainted by centuries of anthropocentrism and religious dogma, rejected by physicists trained to describe how things happen without invoking why. Yet the fine-tuning persists, the eerie precision of constants that permit complexity, the emergence of consciousness from matter, the universe's apparent capacity to know itself through minds like ours. And these phenomena feel purposeful even if no mechanism for purpose has been identified, no agent detected, no intention proven. The ancient philosophical traditions understood this tension, grappling with questions of cosmic order and human meaning long before the advent of quantum mechanics or cosmology. The Greeks debated whether the cosmos was chaotic or ordered, whether the motion of celestial bodies followed necessity or design. And Aristotle proposed that nature acts for an end, that the acorn grows toward the oak not randomly but teleologically, that final causes, purposes, are as real as efficient causes, the push of mechanism. Eastern philosophies approached the question differently, seeing the universe not as artifact but as process, not as designed but as self-organizing. And the Tao, that ineffable principle underlying all existence, describes a reality that unfolds according to its own nature without need for external purpose or divine plan. An order arises spontaneously from the interplay of complementary forces, yin and yang, chaos and pattern, and the purpose of the universe. And it has one, is simply to be, to exist in all its richness and complexity, without justification or goal beyond the being itself. The Buddhist tradition goes further, questioning whether the search for cosmic purpose is itself misguided, a form of craving that binds us to suffering, and proposes that the universe is neither purposeful nor purposeless, but empty of inherent meaning. That meaning arises from the interplay of causes and conditions, from the networks of relationships that constitute reality, and that liberation comes not from discovering purpose, but from letting go of the need for it. Yet modern science, despite its methodological rejection of teleology, keeps encountering phenomena that feel purposeful, that suggest directionality in the evolution of the cosmos. The arrow of time, the fact that entropy increases and the universe moves from order to disorder, from low-entropy Big Bang to high-entropy heat death, imposes a directionality on cosmic evolution, a sense that the universe is going somewhere, even if that somewhere is merely the dissipation of all structure and the triumph of equilibrium. But within this overall trend toward disorder, local pockets of increasing complexity arise: stars, planets, life, consciousness. And these pockets seem to defy the second law, to move against the entropic tide. And while the resolution is that local decreases in entropy are paid for by larger increases elsewhere, the fact remains that the universe produces structure, that matter organizes itself into patterns of astonishing intricacy, and this generative capacity feels purposeful. And if the cosmos is not merely running down, but is also building up, creating, exploring the space of possible configurations, and settling into forms that exhibit novelty, complexity, and the capacity for further creation. The physicist Freeman Dyson, contemplating the long-term future of the universe, proposed that intelligence might persist indefinitely even as the cosmos expands and cools, that consciousness could adapt to environments of decreasing energy density by slowing its metabolic processes, thinking slower but surviving longer. And in this view, the universe is not merely a stage for life, but is structured in such a way that life and consciousness can endure, that the laws of physics permit strategies for survival that extend potentially to eternity. This is a form of optimistic teleology, suggesting that the universe is not indifferent to consciousness, but accommodating, that the constants and laws are tuned not just to permit the emergence of awareness, but to allow its indefinite continuation. And if this is true, then the universe has a kind of purpose, not imposed from outside but emergent from its structure, a tendency toward the production and preservation of complexity and consciousness. And this is where the possibility emerges that purpose is not a binary, either designed or absent, but a spectrum, a continuum of interpretations ranging from blind mechanism to conscious intention, and the universe may occupy a position somewhere in the middle, exhibiting properties that feel purposeful without requiring a conscious designer, structured in ways that invite complexity and self-awareness without being explicitly programmed to produce them. Cosmic natural selection, if it is real, provides one such intermediate position. If the universe evolves through generations shaped by selection pressures that favor black hole production, if consciousness arises not because it is the goal, but because it is correlated with the physical parameters that maximize reproductive success. The multiverse, in its eternal inflation variant, offers another intermediate position where the vast ensemble of universes contains all possible laws and constants. Where consciousness arises in the subset where the parameters permit it, where while there is no purpose in the multiverse as a whole, there is a kind of statistical inevitability to the existence of observers, a guarantee that somewhere, in some bubble, the constants will fall within the life-permitting windows. Emergence provides yet another perspective, suggesting that purpose is not fundamental but arises at higher levels of organization, that atoms have no purpose but organisms do, that particles follow blind laws but ecosystems exhibit goal-directed behavior. And the universe as a whole may be neither purposeful nor purposeless, but a system where purpose emerges at certain scales and in certain contexts as a natural consequence of complexity. Yet the haunting counterargument persists, the possibility that the universe is indifferent, that all appearance of purpose is projection, that consciousness with its goals and meanings and narratives is a local, temporary, fragile phenomenon arising in rare pockets of the cosmos, where conditions happen to permit it. And the vast majority of space and time is empty, cold, purposeless, governed by laws that neither know nor care whether stars ignite or life emerges or civilizations arise and fall. The cosmologist Steven Weinberg famously wrote that the more the universe seems comprehensible, the more it also seems pointless, capturing the tension between the human longing for meaning and the apparent indifference of natural law. The fact that physics describes a cosmos of immense beauty and order but offers no justification for that beauty, no reason why there should be anything at all rather than nothing. And certainly no reason why the something that exists should be structured to produce beings capable of asking why. This is the dread of cosmic indifference, the recognition that the universe may be a mechanism, that the constants and laws that permit our existence are not fine-tuned for us, but simply are. And our presence here is an accident, a statistical fluctuation in the vast space of possibilities, no more meaningful than the specific arrangement of atoms in a particular grain of sand on a particular beach. But there is a deeper problem with the argument from indifference, and indifference itself is an interpretation, a projection of absence where there might be presence, an assumption that if the universe does not exhibit purpose in ways we recognize, then it has no purpose at all. And this assumption may reflect the limits of our concepts rather than the nature of reality. Perhaps the universe has purposes that are not legible to human minds, goals that operate at scales or in dimensions we cannot perceive. And the fine-tuning of constants, the emergence of complexity, the appearance of consciousness, are all part of a process whose ends remain opaque to us, whose logic transcends the categories of intention and mechanism that we inherited from our evolutionary history. The physicist John Wheeler proposed that the universe is a self-excited circuit, that observation and reality bootstrap each other into existence, that the cosmos is not a static object, but a participatory process where observers and the observed co-create each other through the act of measurement. And if this is true, then purpose is not something external to the universe, but internal to it, woven into the participatory relationship between matter and mind, between quantum potentials and conscious actualization. And this is where ancient wisdom and modern physics converge, and the timeless search for meaning in cosmic vastness finds expression in contemporary theories of information, emergence, and quantum mechanics. The Stoics believed in a rational principle, the logos, that pervades the cosmos and guides its evolution, not as a personal deity, but as an impersonal order, a mathematical logic that manifests in natural law. And this concept is not far from the modern physicists' understanding of the universe as governed by elegant equations, by symmetries and conservation principles that constrain how matter and energy interact. The Hindu tradition speaks of Brahman, the ultimate reality from which all things emerge and to which all things return, a consciousness that is both immanent in the world and transcendent beyond it. And while this language is mystical, the underlying intuition, that consciousness is fundamental rather than derivative, that awareness is woven into the fabric of existence, resonates with contemporary proposals in panpsychism and integrated information theory. The indigenous cosmologies of countless cultures speak of the universe as alive, as ensouled, as participatory, as humans are not separate from nature but embedded in it, as this relational ontology, dismissed for centuries as primitive animism, is being reconsidered in light of ecological science and systems thinking, which reveal that the biosphere is indeed an interconnected whole. As the boundaries between organism and environment, between life and non-life, are porous and context-dependent. Yet the truth may be that purpose is neither wholly absent nor wholly present but emergent, arising not at the level of fundamental laws, but at the level of complex systems capable of generating goals, maintaining themselves against entropy, as acting in ways that reflect internal representations of desired future states. A bacterium swimming toward glucose exhibits purposeful behavior, not because it has intentions in the way humans have intentions, but because it possesses mechanisms, chemoreceptors, flagellar motors, metabolic networks, that couple sensory inputs to motor outputs in ways that increase the probability of survival and reproduction. And this coupling is purposeful in a functional sense even if it arises from blind evolutionary processes. An ant colony optimizes foraging routes, allocates workers to different tasks, and responds adaptively to environmental changes, exhibiting goal-directed collective behavior even though no individual ant comprehends the colony's goals. And this emergent purposefulness is real, measurable, predictive, even though it cannot be reduced to the purposes of individual ants or to the chemical interactions that mediate their communication. A human civilization builds cities, develops technologies, creates art and science and philosophy, pursuing goals that extend across generations, shaping the planet and even reaching beyond it. And these purposes are emergent properties of cultural evolution, of the accumulation and transmission of information across minds and time, irreducible to the neural firing patterns of individual brains, yet grounded in those patterns, arising from them through processes of interaction, communication, and collective cognition. And this is where the question sharpens to its finest point. If purpose emerges at higher levels of organization, and it is a property not of particles but of systems, not of atoms, but of organisms and ecosystems and civilizations, and does the universe as a whole, and the ultimate system encompassing all subsystems, possess purpose? The answer depends on whether the universe exhibits the characteristics associated with purposeful systems, self-maintenance, goal-directedness, the capacity to process information and respond adaptively to changing conditions. Some cosmologists argue that the universe is not a system in the relevant sense, that it does not maintain itself against entropy, because it is a closed system and entropy within it increases inexorably, that it has no goals because goals require reference states, and the universe has no outside reference point, that it does not process information in a unified way because the expansion of space prevents distant regions from causally interacting. But others point out that the universe produces structures, galaxies, stars, planets, life, that do exhibit these properties, that the cosmos is generative, that it explores the space of possible configurations and populates that space with forms of increasing complexity. And this generativity, and not purposeful in the intentional sense, is purposeful in the functional sense, structured in ways that maximize the production of novelty and the exploration of possibility. Yet the hope of purposeful existence is shadowed by the dread of cosmic indifference. And the documentary does not resolve this tension but holds it, suspending the viewer between awe and uncertainty, between the recognition that the universe is structured in ways that invite complexity and consciousness, and the recognition that this structure may be accidental, that the laws permitting our existence may be arbitrary, that we may be alone not just in space but in significance. Conscious beings arising briefly in an unconscious cosmos that will continue long after we are gone, indifferent to our dreams and fears and questions. The philosopher Thomas Nagel has argued that the emergence of consciousness in the universe is so extraordinary, so improbable from a purely mechanistic perspective, that it demands explanation beyond the standard physicalist framework, that perhaps the laws of nature are biased toward the production of mind, that teleology is not an illusion but a feature. And the universe evolves not randomly but directionally toward states of greater complexity, awareness, and understanding. This view is controversial, rejected by most physicists as unnecessary speculation, but it captures something many people feel when contemplating the cosmos, that the existence of consciousness, of beings capable of decoding the laws that govern their own existence, is too remarkable to be dismissed as mere accident, that there is something in the structure of reality, perhaps in the constants, perhaps in the laws, perhaps in deeper principles we have not yet discovered, that makes the emergence of awareness not just possible but likely, perhaps even inevitable. And so the section closes at the edge of cosmic purpose, poised between competing interpretations that cannot be conclusively resolved by observation or experiment. But the question of whether the universe wants something, whether the laws of physics were shaped to produce self-awareness, but whether meaning is a human invention projected onto an indifferent cosmos, remains open. The evidence is ambiguous. The fine-tuning of constants suggests purpose, but could be explained by multiverses or necessity. The emergence of complexity suggests directionality, but could be explained by entropy gradients and self-organization. The existence of consciousness suggests that the universe can know itself, but could be explained as an accident of evolution in rare pockets where conditions permit neural networks. What remains, after all theories have been considered, is the raw fact of existence, the undeniable reality that we are here, that the universe has produced beings capable of asking why. After that, this capacity, this ability to reflect, to question, to wonder, is either the universe's greatest accident or its deepest purpose, a feature so central to what the cosmos is that it demands explanation yet resists it, inviting us to live suspended between the dread of meaninglessness and the hope that our existence, after improbable, is woven into the structure of reality in ways we are only beginning to understand, that the universe is not indifferent but participatory, not blind but generative, not purposeless but structured in ways that make purpose possible, that invite it, that perhaps even require it. After that we, in asking these questions, in searching for meaning in the cosmic vastness, are participating in a process larger than ourselves, a cosmic unfolding where matter becomes aware. After the universe opens its eyes and sees itself, after in that seeing, in that moment of recognition, purpose emerges not as something given from outside, but as something created from within, a meaning we construct together, minds and cosmos, observers and observed, consciousness and matter, in the endless dialogue between what is and what asks why. There is a moment, after considering all the alternatives, multiverse, emergence, projection, when the mind circles back to the original suspicion, the one that feels both ancient and unavoidable. What if the universe really is engineered? Not metaphorically, not as an analogy for natural processes that mimic design, but literally, deliberately, purposefully constructed by an intelligence or process or principle that operated before or beyond or beneath the physical laws we observe, shaping the constants and symmetries and initial conditions in ways that would lead, with high probability or certainty, to the emergence of structure, complexity. But conscious observers capable of asking why they exist. This possibility cannot be dismissed on philosophical grounds alone. cannot be rejected simply because it feels uncomfortable or because it recalls discredited arguments from centuries past. Because the question is empirical, testable, a matter of searching for signatures that would distinguish an engineered cosmos from one that arose by chance, necessity, because self-organization. If the universe is engineered, because its design might be detectable in subtle fingerprints, patterns too regular or too improbable to arise naturally, structures that reveal optimization or intention or encoding. The constants themselves, those dimensionless numbers that determine the strength of forces and the masses of particles, might exhibit mathematical relationships that point toward underlying principles or constraints that a designer would recognize, but that seem arbitrary from the perspective of blind physical law. The fine structure constant, approximately 1 divided by 137, has fascinated physicists for decades because its value seems mysterious, not derived from any deeper theory yet critical to the structure of atoms and the behavior of light. And some have searched for numerical patterns or connections to fundamental mathematical constants, pi, e, the golden ratio, that might hint at a deeper logic or a signature of intentional calibration. Similarly, the ratio of the electron mass to the proton mass, the value of the cosmological constant, the hierarchy of particle masses, all of these might contain hidden relationships, numerical codes, or geometric symmetries that would be recognizable as design rather than accident, as message rather than noise. The architecture of space-time itself might carry signatures of engineering, subtle features that distinguish a constructed cosmos from one that emerged naturally. If the universe is a simulation running on computational hardware, then there should be evidence of discretization, a fundamental grid or lattice structure at the Planck scale where spacetime becomes quantized. Then deviations from continuous symmetries, rotational invariance, Lorentz invariance, might appear at high energies or extreme conditions, revealing the underlying computational substrate. Physicists have searched for such violations using data from cosmic rays, gamma-ray bursts, and particle accelerators, looking for signs that the smooth continuum of spacetime is an approximation, an emergent property of a deeper discrete structure. And while no convincing evidence has been found, the searches continue. And the possibility remains that our instruments are not yet sensitive enough to detect the seams in the simulation. The cosmic microwave background, that ancient light from the early universe, might contain patterns, anomalies in the temperature fluctuations, alignments in the polarization, or messages encoded in the statistical properties that could only have been placed there deliberately, or some researchers have analyzed the data looking for such signatures, searching for deviations from randomness that might indicate intentional encoding. Yet the question of how to recognize design is not trivial. Or design in nature often mimics the products of evolution, optimization, or self-organization. Or distinguishing engineered order from emergent order requires criteria that are themselves contestable. Biologists use the concept of irreducible complexity, the idea that certain biological systems are so intricate that they could not have evolved through gradual steps, because removing any component would destroy functionality. And while this argument has been thoroughly debunked in biology, natural selection can produce irreducibly complex systems through indirect pathways, co-option of existing structures, and scaffolding that is later removed. The principle might apply to cosmology. If the constants are interdependent in such a way that changing any one of them by even a small amount would render the universe sterile, and if this interdependence exhibits patterns that suggest optimization for a specific outcome, such as maximizing the production of black holes, and maximizing the emergence of consciousness, and maximizing computational capacity, then this might constitute evidence of engineering rather than coincidence. And this is where future technology becomes critical. And the tools we currently possess, telescopes, particle accelerators, gravitational wave detectors, may not be sufficient to probe the depths necessary to uncover signatures of engineering. Quantum computing, if it reaches the scale and coherence necessary to simulate cosmological processes or to solve problems in quantum gravity, might reveal deeper layers of structure, might allow us to calculate the landscape of possible universes and determine whether our universe occupies a special position within that landscape, a position that would be unlikely by chance but expected if the constants were chosen deliberately. Higher dimensional physics, if string theory or its successors are correct, might provide access to the extra dimensions where the fundamental structure of reality is encoded. If the vibrational modes of strings or the geometry of compactified spaces determine the constants we observe in our four-dimensional slice of the cosmos. If those dimensions bear marks of intentional configuration, symmetric shapes, optimized geometries, mathematical elegance beyond what necessity requires, then this might constitute evidence of design. Cosmological mapping, the effort to survey the universe at ever larger scales and with ever greater precision, might reveal structures or patterns that point toward engineering. If the distribution of galaxies, the properties of dark matter and dark energy, or the topology of space-time exhibit features that are too regular, too symmetric, or too finely balanced to arise from natural processes, or these could be fingerprints of an architect. The cosmic web, that vast network of filaments and voids stretching across billions of light years, arises from gravitational instability, amplifying primordial density fluctuations. But if those primordial fluctuations themselves were not random, but seeded deliberately, but the initial conditions of the universe were chosen to produce a specific large-scale structure. But careful statistical analysis might detect deviations from the predictions of purely natural models. Similarly, if the universe is part of a cosmic natural selection process where black holes spawn offspring universes, if our universe should be optimized for black hole production, if this optimization might be detectable through calculations that compare the number of black holes in our universe with the number that would exist if the constants were slightly different. But there is a deeper problem, one that transcends the technical challenges of detection and touches on the existential implications of living in a designed universe. If the universe is engineered, then what does that mean for our autonomy, our freedom, our sense of agency and responsibility? Does discovering that the cosmos is built diminish us, reducing our choices to the predetermined outcomes of a program we did not write? Or does it elevate us, revealing that our existence is not accidental but intentional, that we are participants in a project whose scope and purpose exceed anything we imagined? The question of free will, already contentious in philosophy and neuroscience, becomes even more fraught if the universe itself is a construction. Because if the laws of physics were chosen deliberately, because the constants were tuned to produce specific outcomes, because the history of the universe, from the Big Bang to the present moment, from the formation of galaxies to the evolution of life to the thoughts occurring in your mind right now, might be the execution of a design, a plan unfolding according to principles established before time began. Yet the fear of discovering hidden purpose is matched by a strange comfort. Because if the universe is designed, because we are not accidents, not random fluctuations in a meaningless void, because products of a process that had us, or beings like us, in mind, the fine-tuning would not be coincidence, but confirmation, evidence that consciousness matters, that awareness is not an epiphenomenon but a feature, that the cosmos is structured to produce observers and perhaps to be observed, to be known, to be understood. This interpretation does not require a personal God or a supernatural creator, but could be consistent with naturalistic frameworks, simulation theory, cosmic natural selection with intelligence, universe-creating civilizations, where the engineer is not omnipotent but advanced, not eternal but finite, a being or process that used the tools available to shape the conditions from which our universe emerged. And this is where the shock of confronting cosmic agency becomes visceral. Because if the universe is engineered, because the engineer might still be watching, might still be present in some form, not as a transcendent deity, but as an embedded intelligence, woven into the fabric of reality itself, manifesting through the laws of physics, or the evolution of complexity, or the emergence of consciousness. The philosopher Nick Bostrom has argued that if we are living in a simulation, then the simulator could, in principle, intervene, altering the laws of physics or the course of history or the contents of individual minds. Then while such interventions might be detectable as miracles, then violations of natural law, then glitches in the matrix, they could also be subtle, seamless, indistinguishable from the normal operation of physical processes. The question of whether such interventions occur, whether the engineer is active or passive, engaged or distant, is not merely philosophical but empirical, a matter of searching for anomalies that cannot be explained by known physics. And the history of science is filled with such anomalies, phenomena that seemed inexplicable until new theories provided natural explanations. And the challenge is to distinguish genuine signatures of agency from patterns that reflect gaps in our understanding rather than gaps in natural law. Yet, even if the engineer exists, even if the universe is deliberately constructed, the question remains whether the designer left a final message, a signature or marker or communication hidden in the fabric of reality, waiting to be discovered by civilizations advanced enough to decode it. This idea, popularized in science fiction, Carl Sagan's contact features a message encoded in the digits of pi, is not merely speculative but follows logically from the hypothesis of design, because if an intelligence capable of engineering universes exists, because if that intelligence intended for observers to arise within those universes, because it might leave evidence of its existence, a calling card written into the constants or the cosmic microwave background or the structure of spacetime itself. Such a message would need to be universal, recognizable to any civilization with sufficient scientific knowledge, independent of language or culture or sensory modalities. And the most plausible medium for such a message is mathematics, the patterns and relationships that govern physical law. And mathematics is the one language that transcends biology and chemistry, that any technologically advanced civilization would discover in the process of decoding how the universe works. The search for such a message has already begun, and not explicitly under that framing. And physicists searching for deeper principles underlying the standard model, for relationships between the constants, for mathematical structures that unify the forces, are implicitly searching for patterns that might reveal intentional design. If such patterns exist, if the constants encode information, if the symmetries of particle physics spell out relationships that go beyond what necessity requires, if the equations of general relativity or quantum mechanics contain hidden layers of meaning accessible only to those who probe deeply enough, then the discovery of such patterns would constitute evidence not just of design, but of communication, a message from the engineer to the engineered, from the creator to the creation, announcing their presence and perhaps offering insights into the purpose or principles that guided the construction. And so the section closes with a soft but powerful cliffhanger, not a dramatic revelation, but a quiet invitation to consider the possibility that we are living inside a question, that the universe itself is structured as a puzzle whose solution would reveal not just how it works, but who made it and why. The clues are there, encoded in the constants that permit stars and chemistry, in the emergence of complexity from simplicity, in the existence of consciousness capable of reflecting on its own origins, and whether these clues point toward design or toward deeper natural principles remains an open question, one that future observations and theories might resolve or might deepen. What is certain is that the question matters, that the search for signatures of engineering is not pseudoscience, but a legitimate inquiry at the intersection of physics, cosmology, and philosophy. And that if the universe is designed, and understanding that design, decoding the message, and there is one, might be the ultimate scientific endeavor, the final frontier of knowledge where we learn not just what the universe is but what it means, who made it, and whether the engineer, having set the constants and established the laws, and initiated the unfolding that led to galaxies and stars and planets and life and minds, left behind a final communication. A word or symbol or pattern waiting in the mathematics of reality, saying simply, "You are not alone, this was intentional. And you were meant to find this message." There is a silence at the end of all the theories. After the hypotheses have been weighed and the evidence considered, after the mind returns not with answers, but with a deeper appreciation of the question itself. After this silence is not empty but full, pregnant with possibility, resonant with the recognition that whether the universe is engineered or accidental, the fact of its existence, and our existence within it, carries an undeniable elegance that evokes both dread and wonder. The dread comes from uncertainty, from the realization that we may never know for certain whether the constants were chosen or random, whether consciousness is fundamental or emergent, whether the fine-tuning points toward design or merely reflects the anthropic selection of the one universe among countless others where observers could arise to notice the tuning. The wonder comes from the patterns themselves, from the fact that the universe follows elegant mathematical laws, that complexity emerges from simplicity, that matter can organize itself into structures capable of reflecting on their own origins, and that we, fragile, temporary, improbable assemblies of atoms, can decode the equations governing galaxies and quarks, can trace cosmic history back to the first fraction of a second, can ask why there is something rather than nothing, and actually make progress toward answering. Perhaps the truest mystery is not whether the universe is designed, but why it gives rise to beings capable of recognizing patterns, questioning existence, and longing for meaning. This capacity is so extraordinary, so statistically improbable from a purely mechanistic perspective, that it demands attention regardless of whether it arose through design, evolution, emergence, or some combination we have not yet conceived. A universe could exist without observers, could run through its history from Big Bang to heat death, without ever producing nervous systems or consciousness or the ability to ask why. And such a universe would be simpler, in some sense, more elegant in its indifference. Yet this is not the universe we inhabit. We live in a cosmos that has produced, at least once, on at least one planet orbiting one star in one galaxy among hundreds of billions, entities capable of understanding quantum mechanics and general relativity, of building telescopes to observe the cosmic microwave background, of constructing theories about multiverses and simulation and cosmic natural selection, of standing beneath the night sky and feeling wonder at the vastness and beauty and apparent intentionality of it all. What if we are the universe's way of discovering its own origins? This formulation, popularized by Carl Sagan, "We are a way for the cosmos to know itself," is more than poetic metaphor, more than inspirational sentiment, because it captures something profound about the relationship between mind and matter, between observer and observed, between consciousness and the quantum substrate from which it emerges. If the universe requires observation to actualize its quantum potentials, if the participatory universe hypothesis is correct, if consciousness is not an accident but a necessity, not a byproduct but an ingredient, if the appearance of beings capable of measurement and reflection is the mechanism by which the cosmos collapses its wave function, determines its history, brings itself into definite existence. In this view, the question of design dissolves into a deeper unity where the distinction between creator and creation, between architect and structure, becomes meaningless because the universe is self-creating, bootstrapping itself into existence through the emergence of observers who retroactively determine the conditions that permitted their emergence. Yet the architect, if there is one, remains silent. No voice speaks from the cosmic microwave background. No message is written in the constants with such clarity that all interpretations collapse into certainty. No intervention occurs that would prove beyond doubt that intelligence shaped the laws we observe. The silence is either the absence of an architect, the universe unfolding according to principles that require no designer, no intention, no purpose beyond the mechanical execution of mathematical law, or the silence is itself a feature of the design, a choice made by an engineer who prefers subtlety to spectacle, who leaves fingerprints in the structure of reality, but no signature bold enough to remove all doubt. Perhaps the architect is silent because direct revelation would undermine something essential: free will, discovery, the value of the search itself. Or perhaps the silence reflects not absence, but incomprehensibility, the gap between human cognition and whatever intelligence or principle or process shaped the cosmos being so vast that communication is impossible, that we could be staring directly at the message without recognizing it, because our minds lack the conceptual tools to decode what is being said. And this is where the fear of eternal mystery becomes acute, because the question of cosmic origins may be one of those problems that humans can approach but never fully resolve, not because the answer does not exist, but because the answer lies beyond the reach of empirical observation or mathematical proof. We can measure the constants, map the galaxies, detect gravitational waves, build quantum computers, but we cannot step outside the universe to see it from the perspective that would reveal whether it is one among many, whether it is simulated or fundamental, whether its laws are necessary or contingent. The observable universe is finite, bounded by the horizon beyond which light has not had time to reach us, and everything beyond that horizon. Other bubble universes, higher dimensions, the hardware running the simulation, is inaccessible, forever hidden from direct measurement, knowable only through inference, extrapolation, and the application of principles like Occam's razor or the principle of mediocrity that are themselves philosophical rather than empirical. Yet the beauty of unanswered questions is that they invite exploration, that the search itself, the process of formulating hypotheses, gathering evidence, building models, testing predictions, generates knowledge and insight even when the ultimate answer remains elusive. The fine-tuning problem has already motivated advances in cosmology, particle physics, and philosophy, has led to serious consideration of multiverses and simulation and cosmic natural selection, has forced scientists to grapple with the role of observers in quantum mechanics and the nature of emergence and the relationship between mathematics and physical law. Whether or not we ever conclusively determine whether the universe is designed, the effort to answer that question reveals structure and pattern and connection that would otherwise remain hidden, enriches our understanding of reality, and demonstrates that human curiosity, that drive to ask why and to search for answers, is itself one of the most remarkable phenomena the universe has produced. Does the illusion of design carry meaning even if no designer exists? The answer may be yes. Because meaning is not solely a property of intentions or purposes imposed from outside, but can arise from within, from the relationships and patterns and structures that constitute existence, from the fact that we are here, conscious, capable of wonder and understanding, participants in a cosmic process that has been unfolding for nearly 14 billion years and will continue long after we are gone. If the universe is not designed, if the constants are random or necessary or selected by anthropic effects, if the appearance of design reflects something about us, our pattern recognition capabilities, our evolutionary heritage, our need for narrative and meaning, and this tells us something profound about consciousness, about how minds work, about the interface between subjective experience and objective reality. If the universe is designed, if the constants were chosen deliberately, and consciousness is fundamental, and the cosmos is structured to produce observers. If the appearance of design is real, a genuine feature of reality rather than a projection, if our recognition of it is participation in a dialogue between mind and matter that transcends the individual and touches something universal. The closing narration zooms out, ascending from the scale of neurons firing in a human brain, through the molecular machinery of cells, past the biological structures of organisms, beyond the planet with its thin shell of atmosphere protecting fragile life, out through the solar system where planets orbit a middle-aged star, across the spiral arm of the Milky Way with its hundreds of billions of suns, past neighboring galaxies and clusters and superclusters, tracing the cosmic web of filaments, and voids that stretch across billions of light years. If the observable universe itself appears as a sphere, if beyond it, invisible, inaccessible, the vast expanse that may contain other universes or may contain nothing. If then descending again, down through the scales, from cosmic structure to galactic to stellar to planetary to biological to cellular to molecular to atomic to subatomic, if quantum fields ripple with fluctuations, if particles wink in and out of existence, if the vacuum seethes with virtual events borrowing energy from the future and paying it back before uncertainty notices. If in this zoom through scales, this journey from the infinitesimal to the infinite and back, the message becomes clear. We are in between, suspended between quantum and cosmos, neither the smallest nor the largest, but uniquely positioned to observe both, to measure the Planck length and the cosmic horizon, to decode the mathematics connecting the microcosm and the macrocosm. The universe might be engineered, or it might be the ultimate accident, but in either case, the appearance of design remains one of the most profound puzzles in science and philosophy. It is a puzzle that touches every domain of inquiry, from physics and cosmology to biology and neuroscience to mathematics and metaphysics. And it is a puzzle that will likely occupy human minds for generations, perhaps centuries, perhaps millennia, driving us to build better instruments, develop deeper theories, explore further into space and time and thought. The final note is not a conclusion but an invitation, not an answer but a call to continue the search, to look closer at the constants, to map the cosmic microwave background with greater precision, to probe the structure of space-time at smaller scales, to explore consciousness and its relationship to quantum mechanics, to ask whether black holes spawn universes, and whether we live in a simulation, and whether the multiverse is real, and whether the laws of physics could have been otherwise. The architect, if there is one, remains silent. If the silence is not absence of meaning, it is space for discovery, room for wonder, permission to search. And in that searching, in that restless human drive to understand, to decode, to ask why, we may find that the question itself is the answer, that the universe's greatest gift is not the presence of design or its absence, but the capacity to wonder about it, to stand beneath stars that are billions of years old and trillions of miles away and feel connected to them, to recognize that we are made of the same atoms forged in stellar cores, governed by the same laws that bend space-time and propagate light and permit complexity to emerge from simplicity. Whether the universe is engineered or accidental, whether consciousness is fundamental or emergent, whether we are alone in the cosmos or part of a vast ecology of minds, the fact remains that we are here, asking these questions. And that asking is itself a form of participation, a way for the cosmos to reflect on its own nature, and perhaps, in the end, that is enough.